This is a very interesting problem, and a couple of reasons why. Because it is not a straightforward clustering exercise. You've all done k-means clustering, and you've all come across data sets where you can just take a data set, do a k-means on it. You've gone through all these techniques, right? Elbow method, silhouette coefficient, all of these things you have seen. This is different in the sense that first you will have to take the data, and first you will have to completely pre-process that data into a different form. So whatever data is given to you now, and that you will only get to know once you click on the download button. You have to click on the download button, and then the Excel file will get downloaded here. I'll just show you for a minute what I'm talking about. And you will get a very true flavor of feature engineering in this exercise, because nothing about this data is right at the outset. So I'm asking you to do clustering on a completely dirty data set. You'll have to start right from scratch. All those things that you have theoretically heard of, like get the data, clean the data, all of these things you have seen, you have to quite literally implement that. If you click on the zip file, and if I open up the Excel file, let us just see what it consists of right now. You will see that my data is present in an invoice level of detail. So whatever data set has been originally shared with me, the data set has been shared with me in an invoice level of detail. So every single row corresponds to a transaction. Every single row corresponds to an invoice. So we have a particular invoice. We know what was purchased, when it was purchased, who purchased it. All of that information we had got here right now. And you can just see the data set. Quite straightforward, not a very difficult data set to work with. But what follows from here is actually the difficult part, which we will come to in the class. So we have got invoice level data. Every single row is like an invoice stock combination. This is the bill number. Invoice number is the order ID. Think of it that way. We have got information about what you purchased, what is the stock code of the item that you purchased, the description of the item that you purchased, the quality, the quantity, how many of these items that you purchased, invoice date when you purchased, unit price, what is the price per unit of the item that you're purchasing, and the customer ID who purchased and where it was purchased. Very simple data set I've got. Your objective is to do customer segmentation on this data. That is all that I have given to you. I'm not going to tell you what to do, how to do. All that is something you have to solution for me. A typical interview will also happen this way. Company will give you a data set. They will not tell you step 1, 2, 3, 4, 5, 6 up to 20. Step 1, do this. Step 2, do EDA. Step 3, remove outliers, all that useless stuff. Companies will not tell you that. You will be simply given a data set. Sometimes even this will not be given. They will ask you to figure out. Data set will be given to you, and you will be asked to solution the problem. And boss, here goes your data. You do customer segmentation on this data. You tell me how many groups and clusters of customers are there. Identify those clusters or groups of customers so that we can do targeted marketing on those different groups and clusters of customers. And this is an extremely important proposition in the world of retail. For some of you who realize this thing, clustering is an extremely important idea in retail, because once you're able to identify the different groups and clusters of customers, then you can target those groups and clusters of customers in different ways, in personalized ways through marketing campaigns, and you can increase engagement among that group. So these are some of the things that actually can be done. Let's say you're able to see that there's a particular group of customers who are regularly coming to my store and they're regularly purchasing products. So that means they are highly engaged customers. They're constantly visiting my store. The footprint is very high. Engagement levels are very high. So next time any kind of new product launches happen, or some of those things happen, how do we involve those customers more into those discount campaigns and all that stuff, right? Or maybe on the contrary, on the other end of the stack, you might have some customers who are you know, you might have some customers who are not that engaged. The monetary value is also very low, and the you know, uh, they're also not spending enough time on the website. So then something is wrong. Why are these customers not engaged? Why? So that is again something that we can again control. We can reach out to those customers differently. So that is the end result of a customer segmentation campaign. So once we are able to segment the customers, then we can target those customers in personalized ways. So just to clarify,
The,
so when we look at a data set, you should never look at the number of rows. Number of rows can be in hundreds or thousands or millions or billions, whatever. So that is okay. That is part and parcel of a project. But what is important is to look at the quality of the data, which is what we do in histograms, right? When you draw a histogram or a distribution plot of a data of a column, you understand what is the distribution of this column, understand what is the distribution of the column, right? So you look at the features, look at the columns, look at the issues in the data at a very high level, without getting into specific row level of detail as to what the values are.
So there are too many missing values in description,
Very
blank
good.
values and some question
Okay.
marks are there.
Would you like to go step by step? Description is one aspect. Description also, I think, for the time being, we will ignore that, because reason being that is actually text data. I think text data you have not seen so far, right?
No,
Have you
sir.
seen text data?
But it
So
can be used as categorical, like value,
we
possible.
not actually. Potentially, some ideas from the description column could be we can extract some details of the product, like keyword extraction we can do, but that will again be part of natural language processing. So for now, for our case study right now, we will not use the description column. But yeah, fair point. Description column has missing values and there are problems in the data. But what are the potential things that we can do?
So
Potentially,
in
what we can do from the description column, we can potentially get some keywords and other kinds of things from that column. Yeah, so those are some things we can actually do.
okay, sir, I also see in quality columns there are some negative values as well.
Quality column, there are negative values. Okay, okay, fair enough. And what does that mean actually? What does that actually mean when you say quantity column has negative values? What is the meaning of it?
The few columns have some negative values, like instead of 6, there are -1 or 4 or something like that.
Okay, okay, okay. And what does that mean? What does the negative quantity mean? Anybody?
Stocks are not available or something like that.
No,
Is it
no,
outliers, sir?
not outliers. No. Negative quantity means what?
Lacking
Invalid
of
values.
Abali, what did you say? Sorry, I missed that.
Invalid values.
Not invalid. Not invalid. What is negative quantity?
or is it something like they have to still order it? So the order is placed, this quantity stock is yet to come, something like that.
No, no, no. Order is already placed. So it's a negative quantity. How is that even possible? Think about it.
So
What is
defaulter,
not defaulter? No, that's not the right term. What else? It's actually a product return,
Oh,
right? Return. So you
Okay.
order 10 items of a product. The quantity will reflect as 10. For that particular order, you purchase 10 units of something. So the quantity shows as 10. But if you return 10 units of something, the quantity will show as -10. Okay. I repeat again, if you purchase 10 units of something, the quantity will show as 10. If you return 10 units of something, the quantity will show as -10. That is what a product return refers to.
so is this a general thing or specific to this data set?
General thing. General thing. Whenever you have a retail data set and you have a negative quantity, that means it's a product return. Because that doesn't count as a purchase. Right? That's a problem very clearly. And how do we handle that issue here? Well, what we will do is that we will remove those cases with negative quantity. Down the line, when I investigate this for further analysis, what I will do is I will simply go and remove all those cases where the quantity is negative. Drop those records. Okay, so we talked about description, talked about quantity. Something in unit price. Did you see some problems in unit price?
There were a few negative values other than that.
There also, which could potentially point to credits. Sometimes you might have a credit in the account, or you're buying a product but you're not having to pay anything for it, or rather you get an extra cashback for it, maybe as an adjustment for another order. Sometimes that happens, right? So big retailers, when you have a B2B or when you're a business transaction when you're doing, oftentimes they will give you store credits. So when you make a purchase, you're not exactly paying anything for it, but it's actually deducted from your store credit. So that counts as a negative unit price. Okay. And finally, customer ID. Any issues in customer ID? I think this is the most interesting discussion, customer ID. So what did you see? Because we are actually doing customer segmentation. So let's come to customer ID. So look at that column. Do you see anything interesting happening there?
More information is required regarding the customers.
More information is required, but do you see any problem in the column per se? When you look at the column, do you see any challenges in the data set? Like first thing, we are actually doing some data analysis, right? So do you see any problem in the data set?
Too many records are missing.
Missing records.
Missing
So-
records. Very good. That's what I was looking for. Very good. Missing values are there. Correct. Now my next question is, what does the missing value even mean? So this is taking you back to some of the stuff that you have done, right? So you see the data set and you explore that, okay, there are missing values in the data. And now we are trying to figure out what do the missing values even mean? So missing value imputation is not an exercise where you take the data set, impute with mean, impute with median. No, that's the last thing. But what we are trying to do here is we are trying to first figure out, A, why is my data missing? And then the next thing we are trying to do is figure out how to impute the missing values. So here first, my question is, what does it mean when the customer ID is missing? So let me just take you back to that again. I'll enable editing and put a filter, and let me just take you to customer ID, and you will see, as rightly mentioned by all of you, approximately 25% of my data is missing. Out of 5.5 lakh records, only 135,000 are present. So approximately 25% of my data for customer ID is missing. So my first question to the audience is, purely from a business perspective, what does it mean when you have missing values of customer ID against this record? What does it mean from a business perspective? How is this data even possible? That's my first question. Then we will see how to handle it, how to impute it. So first part is, why is this data missing? What is it?
Some people will not have IDs for that particular store or something.
Is it don't have items? Okay. What else?
Is it like so anomalous transactions?
What did you say? What was that?
Like anomalous transaction, like some transaction might be recorded without
Uh-huh.
linking with specific customers, kind of things, and
Okay.
or without creating an account, like guest account they created and make transaction.
Okay. Fair enough. I take that point. Absolutely, very well said. Actually, so there are two aspects in which we can analyze this whole thing. First, we can analyze this in the context of offline retail. In the context of offline retail, missing customer ID means that somebody purchased something, but we do not know who purchased it.
Yes.
Okay. So somebody purchased, something was purchased, but we do not know who purchased it. That we do not know, right? So that's the way we look at it. Somebody purchased, something was purchased. Let's say you go to a retail store and you buy something. What happens usually is, at the end of the transaction, they will ask you for a membership card. They will ask you for a membership card, and there are oftentimes there are cases where you do not have a membership card. You say, okay, I don't have a membership card. So if you don't have a membership card, then what will happen at the point of sale outlet? How is that transaction recorded? How is that whole thing recorded when you do not have a membership card? How is that entire thing recorded when you do not have a membership card? How is that thing usually done? So the transaction is happening. The transaction is pretty detailed. So on this particular day, this is what was purchased, this is how many units per purchase, all that is pretty detailed, right? All that is pretty sorted. Now, who purchased it? I do not. This was the order, this item was purchased, this is the description, this is how many were purchased, this is when it was purchased. Who purchased? I don't know. This customer is like a ghost. Why? Because this customer membership card details I don't have. I cannot track that purchase against a specific customer who actually made the purchase. So from the store, the sale happened. I can see the overall sales, what was purchased, but I do not know who purchased. That's the problem. Now, in the case of online retail, as was rightly mentioned by you guys, in the case of online retail, if you think from an Amazon perspective, it refers to a guest account. Guest account is what we are referring to. This is in the case of online retail. So when we talk about it specifically in the context of online retail, we are thinking of it as a guest account. So you're not a registered KYC registered customer. Amazon Pay, when you Amazon, oftentimes they have some Amazon Pay. Amazon Pay is the wallet, and if you know, Amazon also gives you a lot of benefits to access the Amazon Pay ICICI Bank credit card. They're tied up with ICICI Bank, and if customers are looking to buy that credit card, they will give you a lot of offers, discounts, and things like that. So they have this benefit. So Amazon is actually encouraging KYC on their platform. They want to register users on their platform with the proper authenticated government details. They don't want a whole lot of guest accounts because they want to personalize and target the users individually. And it helps in a lot of ways, like fraudulent returns and activities and all that. It helps actually. Like that way, you can minimize. There are often people who purchase something, they return it, and all that fraud happen also. So by doing the KYC and all that, we can minimize these things. Anyways, in the case of online retail, these are guest accounts. We do not know who the customers are. Okay. Now that we know what is this problem, why the data is missing, we know that. Now the next part of the question will be, what do we do with the missing value? How do we impute it? Right? And whenever it comes to missing value imputation, I'm talking about it generally as a topic. Whenever you are trying to do missing value imputation, you should all try to first figure out why the data is missing in the first place. First things first, try to figure out why is the data missing, and then you try to go back and figure out how to handle the missing value. So handling the missing value is the last part, but first you try to figure out why is the data missing. That's the first thing you should try to do. Okay. Now let's come back. Let's come back to the more interesting part of the solution, right? And just to clarify what we will do here, how do we handle the missing value here, friends? We have to drop the data. I'm sorry to say this, 25% of my data, I know that's a massive amount of data. And I know you have seen all those rules like 70%, 60%, all that. A lot of it is just, based on very subjective decision making that we will do. There's no such hard and fast rule that, okay, you will drop it only when this. It is totally based on the business object, totally based on your understanding of the data. So customer ID, wherever the customer ID is missing, it's a ghost. We do not even know who the customers are. So what do? We will go and drop the values. Okay, so what do? How do we handle those records? We will go and drop the values. So 25% of my data will be dropped. I'll tell you the reason why. Because eventually, what is the ultimate objective of customer segmentation? If you look at customer segmentation that we are trying to do, that we are trying to achieve, what is the ultimate objective of it? The ultimate objective of customer segmentation is what? The ultimate objective of customer segmentation here, friends, would be to go back and the ultimate objective of customer segmentation here would be to go back and create groups and clusters of customers so that we can target them individually. We can target each and every group of customer individually for marketing campaigns, promotional campaigns, and all those kinds of things. Send them offer codes. But if I do not even know who the customer is, if they are ghosts, if they are non-registered customers, if they don't have a membership card, how do we even reach out to them? We know nothing about them. We don't know their email ID, we don't know their phone numbers, nothing we know about them. So there's nothing we can do about this customer. We have to drop it. Purely business decision. Now, let me come back to the other more interesting part of the exercise. And here I will get a little conceptual also with respect to what you have studied so far as well in terms of clustering. I'll try to mix the two parts. Remember, right at the outset in the beginning of the class, I mentioned that this case study will be very different. Why? Because you will actually be required to fundamentally transform and fundamentally alter your data. So
Sir?
whatever original, yes, please.
Sir, can we split the data into like online orders and offline orders, sir, just to save some data without losing it?
Not required because this whole data is online retail. If you look at the data set and the data description, this is completely online retail. We don't have to do any of that because the data is given to you itself in an online retail form, right?
Okay.
Already online retail data that is given to you.
Okay. So got it, sir. Got it.
So it is not possible to fill these data with the help of
Nothing we can do. Absolutely nothing. Because, I know we talk about imputation and we talk about mean, median, mode. Customer ID will technically be categorical data. Remember, fundamental thumb rule, whenever you deal with any kind of PII, when I say PII, it's again a very industry specific term. PII stands for personally identifiable information. Whenever we are dealing with any kind of PII, so whenever we are dealing with any kind of PII can never be imputed. Never. You can never predict a customer ID. Don't even try to do it. Anything to do with customer ID, mobile number, addresses, social security numbers, we should never try to impute it. Even if we find some iota of logic, we should never even try because that is a identity information. We can never impute it. Yeah, because we don't know who made the purchase. We have no idea. Could be anybody. It's just a ghost who came and bought something. I don't know. There's no way I can figure out who. Yeah.
Got it.
Yeah. So coming back to the original conversations we had and taking you back to a few clustering problems that you did, and then I'll slowly connect the dots to this exercise. Okay. Uh, so you've all done clustering at a very basic level. Would one of you volunteer and tell me the different types of clustering problems you have done on different data sets? So now in all these exercises, one very important thing that we can relate to is, let me start off with the wine example. If you look at the wine data set, every single row was one instance of wine. Right? In fact, when you, I'll just give you two such features of the wine dataset. Maybe you had the wine dataset, and there were two features that you had. One was the alcohol content in the wine, and let's say the other one was the chlorides content in the wine. There are two features that you had, alcohol and chlorides. I'm just giving a ballpark example. Unsupervised learning, so there are only features, x1, x2 are the two features that you have. These are the features of the wine, or the characteristics of the wine that you originally had. And every row was one wine instance. So wine 1 had this much alcohol, this much chlorides. Wine 2 had this much alcohol, this much chlorides. Wine 3 had this much alcohol, this much chlorides, and so on. So that was the nature of my data set. Now, the way you have all learned clustering so far is you are able to visualize this whole data, right? So you had alcohol along the x-axis. You had chlorides along the y-axis. And there was a very beautiful way we could also visualize our data. Like this is how we have learned clustering, right? So every single dot on a scatter plot is what, friends? What is each and every dot on a scatter plot? Each and every dot on a scatter plot corresponds to an instance of wine. So you can clearly see that hey, this is this particular wine 1 which is having this much alcohol, this much chlorides. This is the wine 2 which is having this much alcohol, this much chlorides. And this is the wine 3 which is having this much alcohol, this much chlorides. So each and every instance of wine, we are able to track how much alcohol it has, how much chloride. each and every instance of wine, we are able to see how much alcohol it has, how much chloride it has. And again, each and every instance of wine, we are able to see how much alcohol it has, how much chloride it has. This is what we are able to track for each and every instance of it. So every dot on the scatter plot is one observation, one row, that is one wine. And then we have done clustering of it. So at the end of the clustering exercise, what did we achieve? We are able to find the groups and clusters of wine. We are able to say that, hey, wine of this are of the same type. Wine of this are of the same type. And wine of this are of the same type. We are able to see different groups or so-called different clusters of wines. That's the inference we are able to make right now. That's what we're able to say. Now, so yeah, so as you can see right now, so we have 10 different types of wine, and we are able to find different groups and clusters of wine. So these are wine which is of one type, this is wine which is of one type, and this is wine which is of one type. Is it a 4 different groups and clusters of 3 different groups and clusters of wine? Yeah, there can be like 10, 15 odd features also. I've just taken 2 for easier visualization, but as Prashant rightly says, the actual data set has multiple features, which is the same thing. We can visualize. But the key takeaway here is every row is one instance of wine. And only then we could do clustering of wines. Let me connect this with the cars example. And every row here, and even if you look at the cars data set, I'm sure you remember we had horsepower, acceleration, cylinders, displacement, and all these kinds of features you have. Every row corresponds to an instance of car. One row is one car. And that is why we could find groups or clusters of cars. And I'm sure you can relate to earthquakes also. Maybe the last example, I'll take earthquakes. And even in earthquakes, I think we have 2 features. One is depth, one is magnitude, if you remember. This is one of the case studies you guys already did. And every row was one instance of an earthquake. So when you eventually go and plot it in a scatter plot, we plot depth along the x-axis and we plot magnitude along the y-axis. And we eventually go and plot it out. Every dot corresponds to one instance of an earthquake. And we can find different groups and clusters of earthquakes. So these are earthquakes which are very similar. These are earthquakes which are very similar. And these are earthquakes which are very similar. So we're able to find groups of similar earthquakes. That's the inference we're able to get. Why am I talking about all this? Because in the current exercise, we are required to do customer segmentation. So we are required to find groups or clusters of customers. So to do customer segmentation, that means to do clustering on customers, we need every data point to be in a customer level of detail. That means ideally every row should be one customer. But is that the case? That is actually not the case. I mean, if you look at this data set, friends, you will see that the customer ID is repeating. You can see that here, the same order, in the same order, 536365, the same customer purchased all this. I think we can relate to it because this happens, right? So you purchase in Amazon and you purchase 8 items, 7 items you purchase. The same customer is purchasing the 7 items. The same customer once again comes back another day and purchases another item. So the customer ID is repeating. So this data set is not a customer level of detail. So every row is not one customer. Every row is actually an invoice level of detail. So in order to do clustering, in order to do customer segmentation, we have to first take this data. We have to convert this data into a customer level of detail, where each and every row corresponds to one customer. We will find out the different features or different attributes of the customer, and then we will go back and do clustering on top of that data. That's the way we will investigate this thing going forward. So take this data set, convert this data into a customer level of detail, group by customer ID, find out the features of the customer. Maybe something like each customer, how much of total money they have spent in the store. So convert it into a customer level of detail so that every dot in that scatter plot is one customer. And once I have that, now I can form groups and clusters of customers. And that is the data pre-processing what you will have to do. Oftentimes, this is the kind of thing that takes a lot of time. So when we say data engineering, data pre-processing, this is what I mean to say. Original data is absolute rubbish that is given to you right now. There's a lot of problems in the data. The data is in a different structure. You have to fundamentally alter the schema of your data. You have to convert it to a customer level of detail, and it has to look somewhat like. Okay, this is what I was referring to in the beginning, that you don't have to do this manually because I'll be eventually sharing this with you. So this is what the final uh, data set will look like. I can quickly come back here and share this with you. You can see this is the original data set which we have the invoice level of detail that we have right now. So what is the potential problem we can solve with this data, by the way? We can do transaction level clustering. And even that is a very common idea, especially in fraud detection algorithms and stuff. People will want to do clustering at a transaction level, right? You want to do clustering at a transaction level. You want to do find out groups and clusters of transactions. Even that is a very common idea. So every row corresponds to a transaction, and you want to find groups and clusters of similar transactions. So these are transactions of one type, and these are transactions of a different type. Maybe which are outliers, and you can identify anomalies of transaction anomalies. Okay, the same way that when you make a fraudulent transactions or a potentially fraudulent transaction with a credit card, the bank will flag it and they will instantly give a call to you saying that, sir, did you make the transaction? Something like that. Transaction level clustering is a possibility, but that is not our discussion here. So we will have to take the data from this form and convert it into something like this form. This is actually called RFM analysis. RFM analysis, where we convert group by customer ID and we find out the recency of the customer, the frequency of the customer, and the monetary value of the customer, right? So we convert this data into a customer level of detail, and we eventually find out what is the recency of the customer, what is the frequency of the customer, and what is the monetary value of the customer. The attributes very different. And if you think about it, what is monetary value? Monetary value is the overall amount that you have spent on the store. Let's say you've purchased multiple things and you purchased an item over multiple days. So we simply grouping by the customer ID. The customer ID is repeating in the whole data set, original data set. So we are group by customer ID we are doing, and we are doing a sum of quantity into unit price. That is how we are calculating it. If you see the code is group by pandas, all the useless stuff we have done. So we are simply group by customer ID and we are finding out what is the total monetary value. Okay. What is frequency? What is the meaning of frequency? Frequency stands for how many times you have made the purchase. So group by customer ID, how many total number of purchases we have done, that is the frequency. So let's say you have placed 15 or 20 orders in Amazon historically, or maybe if some of your older customers, you have probably placed 100 orders in Amazon. So your frequency is 100. If you look at this customer has ordered total 196 times. So group by customer ID counts that, count of invoice and number. How many invoices are there against your name? So 196%. That is frequency. See how we have converted our data to a customer level of detail. And even if I try to represent this data right now, ignore this for a minute. If I plot frequency here, and if I plot monetary value here, every dot on this scatter plot will correspond to one customer. So for this customer, this is frequency, this is monetary value. And now we can, our data set is ready for clustering. Now we can do k-means clustering just the way we know it. The elbow method, silhouette coefficients, and all that stuff will come in. Now we can find what are the groups and clusters of customers from this data. That's what we can do. There's one last level of detail, recency. What is recency? Recency means how many days that you last purchased something. Let me write it down. So recency means how many days back last purchased something. That's recency. And in a way, it tells you the active status of the customer, how active the customer is. Okay, this kind of relates to the active status of the customer, how active the customer actually is. Right? So how many days back the customer last purchased something? So if the customer's recency is let's say 325 days, what it means is the customer last purchased something approximately 325 days back. Okay, if a customer's recency is 325 days, that means the customer last purchased something 325 days back. 325 days back they purchased. That means it's long time back they purchased something. That is their recency. They purchased something long, long, long. That is the recency of the customer. That's the idea. They purchased something 325 days back. That means they are not that active. They are not active. Maybe they are not coming back to the store for whatever reason. On the contrary, there is one more customer whose recency is 0 days. What is the meaning of 0 days? That means they just purchased something today. If I go to Amazon and if I order something just now, maybe I have placed a lot of orders in the past, whatever. But if I just order something now, what is my recency? My recency is 0 days. I purchased something 0 days back. How is that information important, friends? Because using that information, brands will come to know. Using that information, brands will come to know that okay, your recency is a 0 days. That means you're a very active customer. And when I say active customer, I mean to say what do I specifically mean to say with active customer? Active customer, I'm specifically saying that what I mean to say with active customer is that okay, you're very active in the portal. You're very, very active in the portal. That is the inference behind an active customer. Okay, that's the idea. That means you're very committed, very engaged. Whereas if you're a customer who visited last 325 days back, you're not that active. So maybe for these kinds of customers, we need to increase the engagement, maybe give them some more discounts or promotion campaigns. Like sometimes when Zomato, Swiggy, to bring back old customers back to the platform, they will give out offers. Welcome back, 50% off, some of those kinds of things. This is our data set. This is our prepared data set. A lot of data pre-processing stuff here. And I once again say this to all of you very clearly that in a real world scenario, this is the kind of stuff we will do a lot. Companies will not give you the real data. They will not give you the data in the right format. You will have to do a lot of data pre-processing. And this is actually where things get very dirty. And this is actually what case studies are about, right? You will not have everything beautifully given to you. You have to start right from scratch from a real data set, and the onus is on you to explain to your customer or to your interviewer what you will do and how you will approach it. That's the way we have to work with it. That's the idea. So we'll go back and take this data set, and we removed all those issues in the data. We talked about the missing values. We talked about removing the customer IDs, which are missing. We talked about removing the negative quantities, product returns. We don't consider that. All of that we have done. And finally, we have altered the fundamental structure of our data. The data was originally at an invoice level of detail. We've converted that to a customer level of detail. So every row right now corresponds to a customer, and we have the different attributes of the customer. For every customer, we are able to see how many days back the customer last purchased something, how many times the customer purchased something, and what is the total value of customer purchases the customer has made. Right? So we are able to see how many days back the customer last purchased something, how many times the customer purchased something, and what is the total value of purchases the customer actually made. That's the way how we are able to track. Okay, so RFM analysis, recency, frequency, monetary value. All right, wonderful. So now what I will do, I'll be sharing this notebook with you, and until this part of the solutioning is already done, right? And what we will do is now on top of this, we will go back and do our k-means. Okay, so now the rest of the journey is absolutely a cakewalk. I don't even consider that a problem because this was the difficult part. This was the part which involved a bit of thought and some new learnings, I'm sure, out of the way. But once the data is given to you in this form, you will have to do k-means on it. So use your elbow method, use your data visualization techniques, plot the silhouette score, see what kind of silhouette scores you're getting, find out the ideal number of clusters, draw the dendrogram, and finally do the clustering. K means n clusters equal to whatever. And then the last part of clustering that we should always do is we should try to visualize our clusters, right? So do the clustering, find out the number of clusters, do the clustering, and the final step of the puzzle is we should try to visualize our clusters. So we should try to figure out what our clusters mean. So hey, what is this cluster 1 of customers, and what is this cluster 2 of customers, and what is this cluster 3 of customers? What does cluster 1 mean? What does cluster 2 mean? And what does cluster 3 mean? What do these clusters even mean? That is the last part of what we will do here. Okay. Now, whatever RFM analysis that I talked about here, just to clarify, friends, this is not only applicable in the context of retail data. Like use case that we took up here was, more like in a retail context, but this is also applicable in other domains. Like for example, if you think about it, this thing is also applicable from the perspective of, let's say, um, finance, credit cards probably. So credit cards will also be a great use case of this, I would say. So if you look at a typical credit card transaction on data set, every row is one swipe, one transaction, and we have the different attributes of a transaction. So for every transaction, you're tracking what was swiped, how much value was swiped, when it was swiped, what is the merchant category where it was swiped, and all that information will be contained. That is the row level data you have initially, right? Now, what you have to do as part of clustering is you will have to convert this data to a card account level of detail, a customer level of detail, a card level of detail. We can do RFM there. So we can say that, hey, for every card account, we can do RFM. We can find out how many days that the card was lost by. Since are you an active user of your credit card? How many times you swipe the card? How many times you're actually using the card frequency? And what is the total monetary value incurred on the card? What's the overall charge value on the card? Like, what's the total expenses? So RFM can be a very effective tool for fintech domain. You can extend that to UPIs, bank accounts, anything, recency, frequency, monetary value. If a bank sees that a customer is not active, or if a recency value for a particular card account is very high, then what the bank will want to do is maybe proactively reach out to the customer and maybe waive off some fees or something and encourage the customer to use the account. I want to ensure that my customers are using my credit card. If the customers are not using my card, then it's an expense for the bank. I'll give an example. Amazon Pay, ICICI credit card is a free card. And oftentimes when banks issue you a free credit card, mind you, it is not free for the bank. The bank still has to pay the intermediary. So if it's an ICICI Bank Amazon card, it's a Visa card. Visa, MasterCard, and Diners, RuPay, American Express, these are called intermediaries. They are the ones who are taking care of the network. ICICI Bank does not own the network. They're only tying up with Visa. So ICICI Bank has to pay money to Visa to access its network, right? So even though a free card is given to you, but somebody is paying the cost on your behalf to keep that card network active. So it is a problem if a customer is not using the card, if the recency value is very high. And now the next level of analysis will be that, hey, can we use a clustering algorithm to identify these dormant accounts? Dormant accounts means customers who are not active, inactive accounts. And can we target those customers? Can we bring them out and can we make them purchase? Maybe give them some fresh cashbacks. Oftentimes, you will see Amazon, if you have not purchased for a long time, they will give you Amazon Pay rewards, like, do this. Or if you have not used UPI, they will give you a lot of UPI rewards, this percent off, that percent off, and all that. But they encourage you to purchase. The same idea applies for ride-sharing companies, Ola, Uber. Every row is one ride, a transaction, and we can do RFM, group by customer ID, and do an RFM. Every customer we can track how many days back they last took a ride, how many times they took booked a ride, and what is the total value of rides they have taken. So Ola can do customer segmentation on that, identify the creamiest of customers, and also identify dormant accounts where people are not using their cab service. Maybe they have churned over to Uber, something like that. Or maybe even food delivery startups like Swiggy, Zomato can use RFM. So anything where customer segmentation is involved, RFM will be handy. So Swiggy, Zomato, every row corresponds to one transaction. Every row basically corresponds to one transaction, one order that is being placed. And if you do RFM, then you're basically grouping by customer ID. So we can group by customer ID and we can find out, excuse me. So, so we can group by customer ID and we can find out how many uh, days back you last ordered something, how many times you ordered something, and what is the total value of orders you. That's the way how we can do RFM on data. Okay, so there's a lot of use cases are there, and I hope you're all able to get a hang of it. Not just discussing this data set, but whenever you see any problem statement, try to generalize that to the big picture. How can I solve problems in my line of business, in my domain? So always try to generalize it in that context. All right, so I think this is the point where I pick up and I start the conversation with all of you in terms of how we can solution the problem. The initial part I hope was absolutely clear, where we started this data set and we were able to do some exploratory analysis on that. That was the first part of what we did, and now what we will do is we will go ahead and look at the other parts of the solution, how we can actually uh, do the clustering. Okay, so now that we have prepared our data and all those things are done, now we'll see how we can actually go back and do the actual clustering on the data. Okay, so and we will also see some interesting challenges that comes up along the way here in this exercise. Even those aspects we will cover in. All right, so this is partially solved solution step 2. I've also uploaded this in the Google Drive, and the same way I will I'll actually run this notebook. Initial part is very similar here also. In fact, I'll just copy across the initial file names from here so that the original RFM part can be done, and then I can show the rest of the solution to you. All right, here it is. Again, initial part is pretty standard. We are doing the RFM, and this is the part where we have prepared our data, all of you can see, and now we are ready for clustering from here onwards. And let us go with the steps now from here onwards. Okay, let us see that. So first things first, we can do a pair plot on the data just to identify how the distribution of features look like and other aspects around here. So we can do a simple uh, RFM on this data set, a simple pair plot on this data set we can do. And one very interesting observation that we will make is once you do the pair plot, and I'm sure this is something people can relate to. So once the pair plot is done, you will observe that in the pair plot, right? So once the pair plot is done, you will observe that in the pair plot, outliers that are present inside it, right? I repeat again, in the pair plot, the data has lots of outliers. It is still getting generated. It's still happening now. Let me just allow the pair plot to complete here for a minute. It is still getting generated. It's still getting completed now. I think this is still getting loaded. Just let's give it a minute here. And what I wanted to show you is that, okay, I think there's some error I'm getting. Just 1 minute, guys. Okay? Sorry, just 1 minute. All right, here it is. This is what I was referring to. This is the original data set, and we can visualize the feature distributions of the original data. There are 3 columns we have, and once you start to visualize a pair plot, you will see that the diagonals are significant right skews. I think that's expected. So frequency and monetary value are extremely right skewed. That means most customers have average to low frequency, most customers have average to low monetary value, and few customers have very high frequency, and few customers have very high monetary value. That is the inference we are able to make, right? So we can see that frequency and monetary value are extremely right skewed distributions. They are highly positive skewed and they are highly right skewed distributions, right? So most customers have average to low frequency, and few customers have very high frequency. Most customers have average to low monetary value, and there are few customers which have extremely high monetary value. That is the inference we are able to get. So a lot of outliers are there. I think that is expected that most customers will do an average amount of shopping, and there are few customers that will do a kind of a significant amount of shopping. I think that is also par for the course. That's expected also, right? So and the same inference we are able to get even with respect to recency. Even recency, we can see the same thing, right? So if you see the recency part as well, even the recency part we are able to get the same inference. So we can observe that even in the recency part, we can see that most customers have average to low recency, and there are few customers who have extremely high kind of recency. Now, why is this important? Why is this conversation important, and why is it important to talk about the distributions? The reason why this is important is because when you do the k-means on this kind of data, or rather, if your data is highly skewed, and if you just normally do a k-means clustering, mind you, your models will also become highly skewed. One of the common thumb rules is never do k-means clustering on a skewed data, because if you do k-means clustering on a skewed data, you will actually end up creating clusters of outliers. And I'm sure some of you who have proceeded and some of you have pinged me the answers also on chat. So uh, people who have done this, you are actually seeing highly imbalanced clusters. Probably you're seeing something like there's one cluster where there are 15 customers, where there's 70 customers, and there is another cluster where only 2 customers are there. This is called the cluster imbalance, data imbalance, plus imbalance, right? And that's a very clear indication that you have not handled outliers. Because there are outliers in the data, and it's because you are proceeding ahead with clustering without handling the outliers. You are proceeding ahead with clustering without handling the outliers. Because you're doing that, the problem that is occurring here is that what is the problem? What is the issue that is occurring? The problem that is occurring is that the outliers are forming clusters of its own. The problem that is mainly occurring is that the outliers are forming clusters of its own. We are having a separate cluster of outliers. That is what is basically happening. That's the problem. That's the issue that is occurring right now. So we are having a separate cluster of outliers in the process. We have class imbalance basically. So we have got one cluster where 100 customers are there, and there is another cluster where there is only 5 customers, and that's the problem. So one of the key takeaways here would be to first go and handle the outliers. And how can we do that? How can I go and how can we go ahead and handle the outliers here? We can do something like a power transformation, right? Which is just like a log transformation kind of stuff. We can do a kind of a power transform, and by doing the power transform, let me show you what I get. Power transform basically tries to normalize the distribution. So if your original data is somewhat like this, by doing power transform, what we do is we try to normalize the distributions and convert them into a much more symmetrical numerical form. So that is what power transform basically do. Let us do that. Let us do a power transform and see what happens. So I'm doing a power transformation, sklearn pre-processing import power transformer, pt.fit transform, RFM data, and this is the final revised data set I'm getting. I will not get to the mechanical details what is happening, but very briefly, what happens is you raise each of the features to corresponding powers. Like for example, monetary value was right skewed. So what we do is we do a logarithm of monetary value. Frequency is also right skewed. So we do a kind of a logarithm on frequency. So based on the distribution or based on the skewness of the feature, the corresponding data transformation is applied. Okay, so depending on the skewness of the feature, the corresponding data transformation is applied. That is what is actually happening behind the scenes here. That's the way how it's working out. Okay. Now that we have transformed our data, now you can look at the revised distribution plot of the transformed data, and this is how it will look like. We have got recency, frequency, and monetary value. These are the three features we have right now, and you can clearly see the distribution of these three features. They are much more symmetric, much more normal. I'm not saying this is perfect. I'm not saying they are perfect from before, but we are able to see a much more symmetric and much more symmetric normal distribution compared to what we had before. So this is so the original data was highly right skewed or positive skewed, and what you're able to see now is a highly symmetric normal distribution. And there are clusters or peaks that you're able to see in between, right? So you can see that monetary value, there are 3 peaks, and there are some peaks or some clusters that you're able to observe in between also. Now this is our prepared data set. Now we can proceed along, and now we can proceed along with the clustering. This is the usual stuff now with k-means clustering. Now I'm going to just go a little quickly right now because this part you are already aware of. We will do the elbow method. And this is the standard clustering stuff where you can see that I'm plotting the elbow method where along the x-axis I will plot the cluster numbers, cluster number 1, 2, 3, 4, 5, and so on and so forth. Along the y-axis we will plot the inertia. Inertia basically stands for what is the SSE or what is the error in the clustering. And you can clearly see that when the number of clusters is equal to 1, the inertia or the error is extremely high. And as the number of clusters goes from 1 to 2, the inertia drops quite a bit. 2 to 3 drops, 3 to 4 drops. What is the inflection point? It is 2. So just from the elbow method, we can say that the ideal number of clusters is coming out to be equal to 2. How do we say that? Because when we go from 1 cluster to 2 clusters, the inertia has dropped significantly. Inertia has dropped a lot when we go from 1 to 2 clusters. Right? So as we go from 1 to 2 clusters, the inertia has dropped significantly. So we can say that 2 is like an inflection point. We are having a significant reduction in the number of clusters from 1 to 2. Okay, 2 is like an inflection point. Then 2 to 3, 3 to 4, 4 to 5, and so on. That's what's happening along the way. So 2 is the optimum number of clusters. We can get the same inference done using silhouette scores. We can get the silhouette scores also. Let me do that for you. So here I've plotted the silhouette scores as well. And once we do the silhouette diagram, this is still running. Once we generate the silhouette scores, we will get a very similar inference that, okay, for clusters equal to 2, the silhouette score, the average silhouette score seems to be optimal. Silhouette score is one more indication of the cluster quality, right? So higher the silhouette score, the better the quality of your cluster. This is one more indication. So it's still running. And even by seeing this, we will observe that when n clusters is equal to 2, the average silhouette score is the highest. We will see that. You're actually able to see already some numbers coming up. And you can see that in n clusters 2, the silhouette score is 0.4. Now, as you go to clusters 3 onwards, it's 0.31. Go to clusters 4 is dropping even further. So as the number of clusters goes up, the silhouette score is continuing to drop and drop. So for clusters 4, it is dropping. Clusters 5, it is dropping. You can see it's gone to 0.29 now. So the ideal number of clusters is again 2. So with that, we go and actually do the clustering. This is the code for clustering. You can see n clusters equal to 2. And k-means dot fit of x. There is no question of y. Unlike in supervised learning models, we will say fit of x comma y. In clustering, we will simply say dot fit of x. So that means you're applying the k-means clustering on the entire feature set. Feature set this time is the power transformed data. Okay, after doing the power transform, that revised feature set is what we are calling as x. So do the k-means clustering on that. Learn the cluster centroids. We can also print out the cluster centers if I want. And finally, do the predict of x. Predict means for each and every label, for each and every data point, now you find out what cluster value it corresponds to. Okay, so now that the clustering is done, now for each and every data point, we are trying to figure out what cluster it corresponds to. And with that, we can go and plot this kind of a, we can see this in a data frame. So we can see the monetary, recency, and frequency. For every customer, we can see what is the recency, frequency, and monetary value. This we can see for each and every cluster. And we can figure out what group or what cohort they correspond to. So we can say that, hey, customers like this correspond to group 1, customers like this correspond to group 2, and customers like this correspond to group 3. So we can figure out for each and every customer that is present in my original training data, what group or cluster they correspond to. Okay, so this is the clustering we are doing on the training data. And same way, when a new data point comes, we can find out what group they belong to. Now, this is the last part. The best part about K-means clustering is this, where you try to visualize the whole thing as a histogram, as a box plot, right? So observe this data frame, recency, frequency, monetary value, and group. Now we can plot a data frame, by equal to group. So group by this, and do a box plot of the data frame. This is how it looks like. This is the final piece of the puzzle where you can interpret your clusters. Remember, interpretation is the most important aspect in data science. Same holds for clustering. After the clustering part is done, you need to go and interpret your clusters. Hey, what is cluster 0? What is cluster 1? And what is cluster 2? So cluster 0 customers are those kinds of customers whose frequency and monetary value are low, but recency value is high. So who are my cluster 0 customers? Cluster 0 customers are those customers whose frequency and monetary value are low. That means these are customers who are not placing too many orders and who are not placing a very high value of orders. These are customers who are placing less number of orders and who are also placing lesser value of orders. So these are very low engagement customers, I would say, customers in cluster 0. So who are customers in cluster 1? Customers in cluster 1 are so-called high engagement customers. So these are customers who are uh, placing a lot of orders. They're having a very high frequency and they are placing a high value of orders. They're having a high monetary value. So that is what we refer to as cluster 1 customers. Cluster 0 customers have low engagement and cluster 1 customers are high engagement. They're having high frequency and they're having high monetary value. That's the inference. These are customers who are high engagement. Okay? That's the inference we can get. All right, so this is the final piece of the puzzle, and we can also do a dendrogram as well. The dendrogram will also beautifully highlight to you that indeed we can visually make out that there are indeed two groups of customers that are present. They're very clear two groups that are actually showing up. Yes, we can further. The best part about a dendrogram is we can find, I think I can actually run this code also. That will be better because there might be some changes based on the syntax actually. Let me just run the code again. And all of this is just to help you visualize what is the optimal number of clusters. We use elbow, we use silhouette coefficient, and finally, we are using a visual dendrogram to get a sense of what could be the optimal number of clusters. And once I'm sorted that, okay, 2 is the optimum to start with, I'm doing the clustering with 2 clusters. Clustering is not a foolproof exercise unlike supervised learning. You guys have all done supervised learning, classification, regression. You have used grid search, CV, right? Because you had the actual labels that time. You knew what the actual label data is. So you had the liberty and the luxury of comparing the predicted answers with the actuals and adjusting, right? So, but that is something we cannot do here. It is very subjective. And oftentimes the question is that, okay, how do I choose the ideal number of clusters? These are some of the methods. Dendrogram is a visual technique. You have something called cophonetic coefficients, which is a numerical method. But you have elbow method, you have silhouette scores. These are methods which will help you figure out the ideal number of clusters. But ultimately, the actual number of clusters are completely a business problem. What is the actual number of clusters? That is totally a business decision. Okay, so if you look at your whole data set, how many clusters do we really have in the whole data? That is totally a business decision. That's one way to look at it. Okay. You can also project this in a new tab if you want. This is how it looks like. I made it too small actually. So let me. And this is all saved for you in the exercise file. Okay. This is how my dendrogram looks like. All these are visual methods which will help us evaluate the ideal number of clusters. This is one such technique. You can again clearly see that if I go and divide the thread from somewhere here, I can see that 2 clusters will drop. Now, this is not to say that there are 2 definitive clusters. There are 2 very clear clusters. The vertical separation is very high. There are very clear clusters we are able to see. But now, once we are able to identify the 2 clear clusters, we can absolutely find clusters within clusters. Now that we're able to see this, we can find clusters within clusters. Within this, we can see another cluster. Within this, we can see another cluster. We can divide this further into 2 clusters, all that we can do. And that's the best part about a dendrogram. So clustering is a highly subjective exercise. Sometimes business will share some feedback. They will tell you that, hey, I want to see 3 customer groups, because a lot of customer segmentation depends on how you will eventually target them. The marketing team will give some feedback that, hey, we have got 5 different promotional campaigns, so we want you to create 5 different clusters of customers. So a lot of that feedback also comes. It's not purely written in math. Okay, that's another thing to keep in mind. All right. And the last part of the exercise that we will see here, this is another part done, the basic clustering part we have done. And finally, there's one more interesting part that is left out, is PCA. On the same data set, we will see how we can apply PCA. Why? Because if you see the original data now, the way it looks like, so where are we now? We have done RFM, and we saw the data was highly skewed. So we did power transformation, and we did a round of clustering on that. All sorted, all clear. We are able to divide our customers into 2 groups. All good. Now, the problem is, if you look at this data right now, this data seems to be highly correlated. The features are highly correlated. I say features because it is unsupervised learning. There is no output data we have. So the features or the inputs are highly correlated. And specifically, frequency and monetary value seem to be highly correlated. There is a 0.7 correlation that we are able to see between frequency and monetary value. And we know that whenever our data is highly correlated, what do? We apply techniques like PCA or dimensionality reduction. So the same thing we will do here. Now that we are seeing that our data is highly correlated, we will apply PCA on this data, and we will effectively go and now do the clustering on the PCA transform data. How will PCA help? When you have an original data set which is highly correlated like this one, after doing PCA, the correlations will go away. The data will be cleaner, the data will be less noisy, and you will be able to build better quality clusters after doing PCA. So that is the last part of the exercise that we will do. The final thing that we did was we were able to do the clustering, we were able to create 2 clusters. But there was one small problem that remained, and the problem was that even after doing the clustering, what actually happened here was that there was a very strong correlation between the features we had. If we just take a look at it right now, you can clearly see that the frequency and monetary values are showing a very strong correlation. And what do we do now to handle that thing? What do we do now to get into that correlation? So we will do PCA. We will do principal component analysis to take the data now and to remove the correlation and to remove the noise from the data. That is what we will do now. So we will do PCA on the data, and then we will go ahead and do the clustering on the PCA transformed data. So that is how we will actually approach it now. So let me run this for you. I think let me just show you directly. Nothing to solve now. This is the initial part we did. We already created 2 clusters, and we were able to see 2 very clear clusters in the dendrogram. And now we will apply PCA on the data. Look at the code, everybody. Now we all know that if the original data has 3 dimensions or 3 features, then after PCA will also create 2 features, right? If the original data has 2 features, even if you do PCA will also create 2 features in the process. If the original data has 3 features, and if you do PCA will by default create 3 features. 3 dimensions or 3 features will be created if you are doing PCA. Okay, so if you do PCA effectively, 3 dimensions or 3 features will be created if you go and do PCA effectively. That is what will happen, right? Now the thing is, we want to restrict it to 2 principal components. If I want to do that, we can say n components equal to 2. And this we can do using explained variance ratio and all those kinds of things, right? So we have all those metrics using which we can do it. So we take n components equal to 2. And if you do that, this is the best part of PCA. You can see the correlations will completely vanish. Mind you, initially we had recency, frequency, and monetary value. And if I have to just write it down for you for a minute, if I just show you this for a minute, I'm sure all of you have heard of PCA. And just for a minute, if I take and show you what's really going on to summarize the conversation. So original data, we had recency, frequency, and monetary value. This is the original 3 features we had. And after doing PCA, by default, we end up creating PC1, PC2, and PC3. So from 3 features, we end up creating 3 principal components, 3 derived features we create, right? And then Out of this, we can do dimensionality reduction, and we can choose the top two or the top one principal component based on explained variance. So we can use certain thresholds like, okay, consider all those features such that the explained variance is equal to this and so on and so forth. So we can do all those kinds of stuff, right? So here I've taken only two. Out of the three features that are originally created, I have considered only two out of them. And this is the visualization you're able to see of the principal component features. This data you're able to visualize. And you can clearly see that although the original features were demonstrating a very strong correlation between them, but after we did PCA, the correlation has completely vanished. And we are very confident that now if I go and do the k-means clustering on this data, if I do the k-means clustering on the PCA data, we will end up creating better quality clusters. Okay, and you can see the explained variance ratio also mentioned here, 70% and 22%. Approximately 92% variance is explained in the first two principal components. Okay, even better, even if you take the first principal component, like if I take only one principal component, a whopping 70% variance is explained only in the first principal component, which is what we will actually do. So from these three features, we will by default create three principal components. We will narrow it down and restrict it down to one principal component, and then we will finally do the clustering on this one principal component. This is where we have finally taken the problem to. So we effectively have only a single dimension, and we will do k-means clustering on this single dimension. So it is like saying we have got a single PC1 dimension. The data points are all organized like this, and we will basically find out the cluster centers in this dimension. Okay, so that is what we will do now. And believe it or not, we will actually end up getting better quality clusters. Okay, so this is what we will do. So, so let me show you for a minute. I have to actually run the code. Sorry, I think I didn't execute the code here again. Let me just take it. I'm also sharing the code along with you as I'm coding. I hope the big picture idea is clear. Again, one of the things I always encourage in my classes is the overall understanding. Because today we live in an era where writing code is useless. You've got LLM models and GPT based chatbots which can generate the code for you. But what machines are still lacking today is reasoning power. You can't give a problem and the machine can't write the whole code for you. You have to tell it what to do. So the understanding and the overall solutioning part is very important. Once you know what is it that you want to do, the code can take over. You can have the machine write down the whole code for you. Okay. I'm not saying that you should not know anything about coding, which is what we have encouraged you all through the program. We have taken you through lots of exercises hands-on, but then the overall understanding is far more important than just writing code. So let me quickly execute this once again for you. Sorry, I'm doing this again, guys, because I wanted to actually show you the whole solution from scratch, and I want to show the PCA part also. I've broken it up into three notebooks actually. That's why I have to do this separately every time. And finally, I'll just take the file name. I think we are good after that. Just a minute. Okay. This is the final file, which is online retail solution. And this is where the whole thing is done. The end-to-end part, starting from the raw data, doing the RFM, doing the clustering on the original data, and then finally doing the PCA, and then repeating the clustering after doing PCA. So what is the main takeaway from PCA here? That after doing PCA, we have removed the noise from the data, remove the correlations from the features, and thereby we can build better quality features. That is the takeaway from what we are getting after doing. Let us see. All right. Now, continue. going to take a while here because the initial part is actually taking some time, the part where I'm loading the data. It's going to take a minute here. All right, so we'll quickly complete this one now. RFM data frame generation part. And after the RFM part is done, this is the initial clustering we have done. Remember, we have also done power transform. Why power transform? Because we want to remove the outlier impact. And we can also follow it up with a round of scaling. This was an original question people asked me. Why have I not done scaling particularly here? Because after doing power transform, eventually the data is getting scaled. Now, it's not actual scaling that is happening, but you can see the range of the values right now in the pair plot. It is coming within a reasonable range of -2 to +2 kind of thing. This is after power transform, but actually you should still do scaling. After power transform, you can do a round of scaling, a standard scaler to convert it between -2 to +2. You can follow it up. But in this exercise, it does not make a difference because anyways, my data is coming in the right range, but that is not necessarily going to be the case, just to clarify. Okay. So then we are doing the clustering on the original data. This is the k-means clustering we have done. And after that, we have applying PCA. And I told you we will stick to principal components equal to 1, n components 1. I will take that because we saw that with n components 1, we are able to represent 70% of variance. So I will take n components 1, do the PCA, and then I will go and effectively repeat the entire clustering exercise after taking n components equal to 1. Okay, so after taking n components equal to 1, I will repeat the whole exercise again. So now I have a single feature called PC1. Now I have a single feature called PC1, and I will repeat the whole clustering exercise only on PC1. So that is including the elbow method, the Sweetviz codes, and the dendrogram. And I'll show you after this code executes successfully. I'll show you that how each of the three things improve. The dendrogram will become better. The elbow method will become better. You will see a very clear bend showing up now, and even the Sweetviz codes will show higher values. Okay, and we'll see that. We'll see that comparative understanding in a minute. Okay, so you can see here also iteration 1, when we were doing the original analysis, the elbow was getting bent only at 2. At 2, I was seeing a very clear bend. But after I do PCA, you will see that the bend will start to show at 3. You will see that. You'll be surprised with the results actually. Okay, so once you see, it's still running. The dendrogram is actually a very, very compute intensive process. It's still taking some time. And after this happens, after the PCA part happens, you get to see that the elbow method, the part where I'm doing the elbow method, you will clearly get to see that the elbow will start to show a bend at 3. Okay, you clearly see that. It's not happening here, but let me just run this with n components equal to 1. Let me see that. Allow me a minute, guys. I'll share this code. All this is in the Google Drive. As in when I'm running the code, I'm also saving it for you, so you can access the same code snippets in your Drive link. Yeah. All right, here it is. So I've done the PCA, you can see right now. And now I will quickly do the the elbow method after doing PCA. So we are actually repeating the whole exercise only with respect to a single principal component now. And let us see how the elbow method will look like. We'll actually get to see that now the cluster will start to form at 3. Look at this. This is what I was trying to show you. Okay, so clustering is an exercise where we are trying to discover clusters which are already a part of our data. So after we do the PCA, the data quality has become better, and you can clearly see that at n clusters equal to 3, we are able to see the components a lot more clearly. Okay, so at n clusters 3, the inertia is all of a sudden dropping a lot. This was not visible before. This particular pattern was not visible before, and after doing PCA, we are able to visualize that particular pattern. Okay, so that's the learning that we are able to have. Finally, we can also see what's going on here. Let us observe that also. So we can go back and take a look at the silhouette scores as well. Let us quickly look at the silhouette numbers. Remember, the silhouette scores were only coming around 0.4 before, something around that, and now you can see the silhouette scores, how it works out. Okay, even the silhouette score values would have significantly increased, actually. So what is my revised data set? Just 1 minute, guys. Data frame X, just 1 minute. Okay. So PCA, PC1. Okay, we only have a single column, that is PC1. Sorry, I only have a single column PC1 right now because we only have a single feature. And let me just do this one. Yeah, okay, so expecting one input. Just 1 minute. It's Android. Just 1 minute. So all that I'm trying to do is I'm trying to repeat the same exercise with respect to a single dimension. So we have done the PCA fit transform X, reassigning it back to X. All right, this is all good. This is all fine. This is the clustering we have done on X, which is also okay. And we can see the elbow method is also coming absolutely fine. It's showing a bend at 3. Here, just a minute. N clusters 2. No, I think I'll do N clusters 3. Sorry, that was the problem. I'll say 3 because we're able to see 3 clusters, right? Yeah, so all good. So we're able to see 3 clusters, and these are the 3 cluster values that you're able to get in the process. Okay, all right. I think there's some variable that's going for a toss here. Just 1 minute. Let me just check. X underscore df. Just a minute. Let me quickly look up my X1. So I think what happened here is that there's some variable I took, and I think I overwritten that variable here. So X is the original array. This is basically the one principal component I've taken. So if I just go and do pd.data frame of X, I can actually see what is the shape of this. I think this will be only a single column. Oh no, it's actually taking 3 columns. That's interesting. This is where the problem is. Why is it taking 3 columns? After n components 1, right? I think this is where I think this is capital. No, this is capital X only. That's where the problem is. That's where the problem is. Okay. Okay, let me check what went wrong here. Now it's fine. I think I did not run this correctly. Now you can see it's fine. Now it is perfect. So we have a single principal component, and now this is my data frame. And I can plot the pair plot on this particular data frame. Now this is okay. This is the explained variance ratio, and this is principal components underscore. We're able to see that. Okay, I think now we are sorted. Great. Let's just look at the code here. This is the k-means one that I've done, and I can visualize the clusters. That's also, I think, they are good. Another thing, next thing that we have to do is we have to go and I will do dot fit of X and dot predict of X, get the labels, and we can also print out the cluster center. Let me just run this code again. I think that now it's fine. Now it's absolutely clear. It was not working fine before. So now we can see there are 3 centroids I'm able to get, and single dimensional centroids actually. We're able to see that. And finally here, let me just take a look at the code. PC1 is one single column I've got, and dot predict of X. So there's I'm assigning it back to predictions. Predictions is the column where I will keep the prediction value, and I'm taking a data frame. The data frame will consist of two columns. One is x. X is nothing but the original feature, the feature that is x, and the column names equal to call names. This is what we have here. Let me run this, and we can look at x underscore df.head. I think now this will look good. Yes, this is more like what I wanted. This was not coming right before. So PC1. So this is my transformed dimension that we have right now, and we can also see the cluster labels: group 0, group 1, group 2. Okay, and we can do a pair plot. We can do a box plot to visualize that particular data. Now we are sorted. Now we are sorted. Now we can do all this stuff here. Okay, and we can clearly see that the clusters are highly segregated across the principal component. Okay, you can see that beautifully. You can see a beautiful separation between the clusters. So very clearly, TCA seems to have helped. The objective of clustering is to create distinct and compact clusters. So different clusters should be distinct between them, and the same cluster should be very compact. It's objective of clustering is to create distinct and compact clusters, which we are able to achieve right now. Okay, and now the last part, I wanted to show you the silhouette scores, and the silhouette scores part is maybe a bit of a problem. So just give me 1 minute. This was not working fine before, I think. Just give me 1 minute. Just allow me 1 minute. Let me look at the code once. X underscore df dot graph x value, x value in x, this is assigning in y. This is all okay. Cluster numbers is all the way from 2 to 8, which is also okay. Just give me 1 minute, please. All right, this is all good. This is all good. And we have to just look at the cluster values. Okay, I'm not interested in plotting it out. All I want to do is just to see the cluster values. So what I can do is instead, yeah, all this I can actually remove. This is not needed because we don't want to visualize the thing. Visualization part is not required because honestly, we don't have two dimensions. We only have a single dimension, so we cannot visualize firstly. So this particular part of the code can be easily dropped. Okay, I hope you're able to observe how we are making the changes. I'll just go and drop this part of the code. This part is okay, and in it, clustering part we are done with predict of x. This part is okay, looks good. Silhouette score I'm computing, and here I'm printing out the silhouette scores. This is also good. The sample silhouette values I'm also computing. This is also good. All right, great. So y in lower, this is the visualization part. Again, I don't care about this. I'll go and remove this. So the code will become a lot smaller right now. This is all useless stuff, not required. Okay, this is matplotlib stuff. You don't need to plot all this. You just need to see the values here. Okay. Rest I think is fine. Clusterer and all this is okay. Let me run the code. Now I think there's some problem. Unexpected indent. Where did we get one? Anybody's able to see that? Oh, did I remove the for each loop? Oh my god. My god, what did I do? I think I removed the for each loop. Huh? Sorry, by mistake I removed the for each loop completely. Why will I remove the for each loop? Yeah. Sorry. Okay, let me just go and do this again. This and all is not needed. You can just remove all these labels and all. And this is pretty much what we have here. That's it. Rest all the code can go. You can look at it later. I'm just making the modifications real time in the class. So you can actually see this later, what I've done. And this is all matplotlib. So the code might look a little scary for Silhouette's code, but you can see the major part of what I've done is just matplotlib stuff. And now we can see that n clusters 2, we can see the Silhouette scores is 0.59, n clusters 3, 0.57, n clusters 4 is 0.52, and so on and so forth. So very clearly, you're able to see that after doing the PCA, after we are able to successfully do the PCA, the cluster quality has become better. And how do we know the cluster quality has become better? Because the Silhouette scores have increased. Because the Silhouette scores have increased, we can say that the cluster quality has become better. The quality of the clusters have become better right now. So we are looking at a Silhouette score of 0.59 right now. So the cluster quality has become significantly better right now overall. And now we can do agglomerated clustering. The same data set, we can do agglomerated clustering. We can see what patterns we are able to decipher from that. Let's see, X is my data frame. This is okay, all good. And you'll be in for some surprises. Fingers crossed. Let's see. Let's see this one. What we're able to see once we do agglomerated clustering. Let us see that in action. And you'll be surprised to see that you'll be actually surprised to see that again, 3 clusters will become very clearly visible. So previously we were only getting 2 distinct clusters that were visible, but now after doing the PCA and after repeating the exercise after PCA, all the indicators are showing that the quality of my clusters have become better, and we're able to discover more clusters in the data. Not just the original 2 clusters, but we're able to discover more clusters in the data. So that is the takeaway. And after this is successful, we'll see the dendrogram and we'll observe that even the dendrogram will show us 3 clusters. The 3 clusters will be very clearly visible there also. We will see that. All right, this will just take another few seconds to generate. Any questions? I hope all of you got an idea. This was an end-to-end conversation I wanted to have with you. Complete case study involving a completely raw data set that was not at all prepared for us, and we were able to do some analysis and some beautiful clustering and PCA on top of this data. This is the dendrogram, how it looks like, the final piece of the puzzle, and you can clearly see that how beautifully we're able to see 3 clusters. So 2 very distinct clusters, no doubt on that, friends. 2 very distinct clusters we're able to get from the data. And then you're able to further divide that into 3 clusters. You can see even if I cut the thread from here, 3 clusters are dropping, the orange, the green, and the blue. So we are able to very accurately divide our data into 3 buckets. Now we can further argue that we can see clusters within clusters. So when I see the orange cluster, you can probably say that, okay, I can further divide from here, and I can further divide that into subclusters. So that can also happen along the way. Right, I hope it's clear. Everybody's getting a hang of it. And this is pretty much the case study I wanted to show all of you. Okay, this is one case study that I wanted to show all of you. So the whole code is saved. You can go back to your Google Drive online retail case study, and all the documents are here for all of you. Okay, I hope you're good. Yeah. All right. Now we'll go to one supervised learning workflow. Some new learnings there also we will see. Some new ideas we will discuss, and we try to make it a little interactive because this was a very hands-on intensive class. So we'll try to make it a little interactive with some mini case studies, and then we'll go to one more exhaustive supervised learning case study along the way. That's going to be the plan. Okay. Any questions? I'll pause for a few minutes for any questions you might have. You can come on audio and ask me. Okay. It gets too boring if you just type. So come on audio, speak up, and ask questions. There was one very interesting visualization I wanted to show you. This is one of my favorite visualizations when it comes to PCA. I'm not sure if you have seen this in the classroom. Somebody's talked about it, but you can refer to it. So it's a pretty nice one. This is setosa.io visualization where you can actually visualize that how by doing PCA we can see the clusters better. So this is my original data, and you can see the after I do PCA effectively, these are the principal components PC1, PC2, PC3, and along the first principal component, the clusters are very clearly visible. So the original data across X, Y, and Z, the clusters were not that clearly visible. But after I do PCA, once I do principal component analysis, we are able to visualize the clusters very accurately because much of the information is now present and constrained only within the first principal component. So all of that thing we are able to see only within PC1. So all the data points are now clustered within PC1. We are able to very clearly visualize that. So PC1, in clearly there are 3 groups or 3 clusters of data. Right. So this is a very handy piece of visualization I wanted to share with all of you. So please look at that, everybody. All right. So this is again a very interesting problem statement. This is in the context of cab rides and how cab companies like Ola, Uber, they look at the different attributes of the ride and try to predict the fare of the ride. It's more of a use case discussion, and it's again an excellent example of feature engineering. How the original data is in a completely raw, dirty format, and how we go and convert the data into a processed format. That is what we will see. through feature engineering, right? We will see that. The fare prediction part, actually, how the fare is automatically predicted, actually, you can see that. Now, the original data that you see right now is given in this form, okay? Pickup date time, that is the time when you're booking the ride. The timestamp will be computed from your phone. Pickup latitude, longitude, drop off latitude, longitude will be the GPS coordinates of the pickup location and the drop location, which is again what we say as a passenger before we book the ride. And the passenger count. This doesn't happen in India, but in other countries, many countries, what you have to do is when you book a ride, you also have to specify how many passengers will sit in the car. And that is also an important attribute. It is not like you've got a car, so let's stuff 7, 8 people in the car and go. No, obviously. So more the number of passengers, more the weight of the car, more the weight, and definitely the fare will increase accordingly because you're carrying more passengers. Now, what we do here is we take the original data, whatever original data we have, we take that, and we go and convert that original data into a process numerical form. Okay, that's the next thing that we do. So we take the original data and we try to convert that into a numerical form, into a different form, and we will see some feature engineering techniques along the way. Okay, what is the specific problem that we are trying to solve here? We are trying to predict the fare amount. So what is it that we are specifically trying to predict the fare amount? That makes it a regression problem. So whatever you are seeing right now, this is a classic example of regression. We are looking at the different features of the ride, and based on the different features of the ride, we are trying to predict what is the fare of the ride. So we are doing a kind of a regression problem on this. So based on the different features of the ride, we are trying to predict what is the fare of the ride. It's a taxi fare prediction problem. The regression exercise that we are trying to solve. Fare prediction is what we are trying to do. Based on the features, we are trying to predict the fare. So first things first, generally what is recommended, generally what we do in the industry is we go and always build a baseline model on the original data. That is the first thing that we always generally try to do. So whatever data is there, you take the data as is and try to build a baseline model on the original data. That is exactly what we will do now also. So we will take the original data as is available right now, and we will go ahead and build a baseline model on the original data, which is what we will do now. No data pre-processing, nothing we will do. We will simply build a baseline model with the raw features. And here I am using XGBoost regressor. Rest of the code is straightforward, fit and predict, and we are calculating the R square. And we are able to clearly see that we're getting 73% R squared with a baseline model. And this is oftentimes a very important thing that we should do, because oftentimes we worry about a lot of data engineering, feature engineering, all that. But one thing that we should do right up front is whatever is available, although the data is garbage, a lot of problems are there, but just build a baseline model. Let's do that. These are called experiments. We always do experiments along the way. Experiment number 2, what we will do now is a lot of outliers in the data we are seeing, right? If you see fare amount, so I'm just plotting the distribution of fare amount. You can clearly see that fare amount consists of a lot of outliers, lot of skew. It is generally a right skew distribution, which is understood. Most of the fares are average to low, and few are extremely high. So there are few cab rides where the fares are very high, and there are other cab rides where fares are negative. We're able to see that also. So we are seeing a extremely right skew with respect to fare. We can see that. Similarly, if you look at latitude, longitude, you can observe that there are a lot of outliers with respect to latitude, longitude coordinates also. There are some latitude, longitude coordinates which are extremely high, extremely low, and those could be potentially due to GPS malfunctioning. You're booking the ride from somewhere and the ride is picked up from a different location. Very common, can happen. Iteration number 2 or experiment number 2, what we are doing is we are removing the outliers. We are removing the outliers and we are building a baseline model after outlier removal. See how we are going in steps. So machine learning is not a one-time approach where you do something and you build a model and that's it, everything's over. No, we always conduct experiments and different experiments. We treat our data differently, build another model. So the model building process, this is the reason why it takes time. It is not like a one-time process. It's an iterative process. You build a baseline model, make some changes, once again rebuild the model, make some changes, rebuild the model. So this keeps on happening over time. That's experiment number 2. And you can see that in experiment number 2, we are getting a slightly better quality model. So the R2 score has become 0.76 now. So what is the R squared now? It is 0.76. So we apparently have a better model than what we had before. So the quality of the model that we are seeing now is better than what we had before. It's a 0.76 R squared value that we are seeing right now on the screen. So I repeat, we have a better model than what we had before. Moving on, experiment number 3, we have a timestamp column. Timestamp column per se is not that useful for analysis. And what we are trying to do is we are trying to create a lot of temporal features or time-based features from the timestamp column. So we have the date and time column. And from the date and time column, we are trying to create temporal features. So we are trying to create a lot of temporal features from the date time column. And temporal features here could be year, month, day, hour, day of week, and so on and so forth. So it is like from the timestamp, you're calculating the year, you're calculating the month, you're calculating the day, you're calculating the hour, you're calculating the day of the week. So these are the temporal features that you're calculating from the timestamp column. Now, all of what we are trying to do in this entire feature engineering process, and something that I'm sure people in this audience know, that ultimately we are trying to generate features which will be better predictors of the output. Output, remember, is fair amount. That is what we are ultimately trying to predict. So the overall objective of the solution will be to try to create features which are good predictors of the output. The timestamp per se is not a very important predictor of the output. Timestamp is not a very useful column, but we are trying to create features which are good predictors of the output. That is part of what we are trying to achieve. So once again, we are trying to create features. We are trying to generate features which are good predictors of the output, as I said. So timestamp is an example here, obviously. But yeah, we're trying to create good quality features, just to clarify. Good quality features we're trying to create. So year is a feature we create, month is a feature, day is a feature, hour is a feature. These are the kind of features we are creating. And this is with the hypothesis that keeping other factors constant, year is a good predictor of the so keeping other factors constant, we can say that year is a good predictor of the fair. The hour of the day is a good predictor of fair. Keeping everything else constant, we can say that the hour of the day is a good predictor of the fair amount. If I know that the hour of the day is between maybe midnight to morning 6 o'clock, the fares are typically going to be very low. And I don't know, from morning 6 to or morning 9 to evening 5, the fares are typically very high. The very clear distinction of the fare based on the hour of the day. So we can say that this is a good predictor of fare. Keeping other factors constant, if I know the hour of the day, we can predict the feature accurate. We can predict the fare accurate. So hour of the day is a good predictor of fare. That's the inference we can draw here. So morning the fares are different. Evening or night time the fares are different. So the hour of the day is once again a good predictor of fare. Day of the week is a good predictor of fare. Keeping other factors constant, if the day of the week is Monday to Friday, the fares are typically going to be high. And keeping other factors constant, if the day of the week is a Saturday, Sunday, then the fares will be low. So just by creating these features, we have created better quality features, because now with these features, we can more accurately predict the fare. Same apply for month. Now, month is also a good predictor of fare. You might be surprised or curious how, because monsoon seasons in Bangalore are a nightmare. I'm sure some of you probably will be from Bangalore. So if it's a monsoon around July, August, September, if it's raining very heavily, the Bangalore roads come to a standstill. The same applies to other parts of the country. Nothing against Bangalore. I've stayed in Bangalore for 14 years in my life. So same for Bombay, same for other parts. So generally, when there is rainfall, if you try to book a cab ride, the fares will be high. Why? Because it correlates with time. The driver will take a lot of time to reach the destination, and the time adds up. There is traffic, so to compensate for that, there's more demand because this rainfall, people cannot take a public transport. Most people will want to book cabs. So generally, during certain months of the year, um, the fare is high. Other months of the year, the fare is probably low. It will be some very slight correlation you'll find. So this is again a good set of features we have created. And by creating the temporal features and by building the model, experiment number 3 we are doing, you can see that we are getting a better analysis, 77.5% output. So this is what I wanted to highlight, how you start off with a data set, you build a baseline model, and how do you continue uh, doing feature engineering? How do you continue iterating through different approaches? And how do you create better and better quality models in the process? So that's the thing I wanted to clarify. Okay, how you actually do it. All right. I hope this is clear. Everyone's sorted. Everyone's getting an understanding. Moving on. We can predict, not predict, find out. Correct. That is one approach, feature selection. So what I am doing right now is just to do feature extraction. Prashant, feature selection will only come in handy when you have lots of features. If I have a data set with 100 features, then what you said applies. We can apply p-values and feature importances to identify which are the most significant features. Problem right now is I don't even have features with me. I have a data set with only 2 or 3 features, useless data set we've been given. So now we have to use domain knowledge to create features. Like for example, we have latitude, longitude. Now latitude, longitude per se is not useful. What I need to do is I need to take latitude, longitude and create distance, which is what I'm doing. I'm creating a distance feature, and the moment I create a distance feature, my R squared goes up to 83%.
Yes, sir.
These are the kind of feature extraction that I'm doing, feature engineering, feature extraction. Feature selection comes in handy when you have lots of features. And now we are trying to figure out, hey, which are the ones I should pick.
Yeah, okay, sir.
Distance will be an important one because, again, as I said, keeping other factors constant, distance is a very important predictor of fare. Obviously, more the distance, more the fare. And the different ways distance metrics can be done. Google APIs can be used. Google charges you. Companies like Ola and Uber, they pay Google a significant amount of money. That's why Ola is moving out of that. If you've seen Ola, they have got this company called Kruthrim AI, and they're moving away from Google Maps now. So they've got their own in-house open source mapping system that they have got now. They're saving a lot now. If you want to use some open source maps, what you can do is you can access OSRM, OpenStreetMap. These are some exciting projects where you can actually access open source map data. So this is Project OSRM, very similar to Google Maps, but it's not as real time, not as dynamic. Doesn't give you traffic information, but it does the job. So this is Germany, and let's say if I want to travel from a place in Munchen somewhere here, I want to travel from here all the way to, let's say, somewhere here. I can do that. It'll, as I said, it will mostly do the job, but it will give you the distance. What I'm interested in is to find the distance. That hey, if I want to go from latitude, longitude, so and so to latitude, longitude, so and so, how much distance I have to travel? So I can calculate the distance based on the pickup lat long and drop of lat long. I can find out the exact distance that I have to travel. That can be done. The distance can be easily computed. Okay, so that is something that can be done. And if you see here, more the distance, generally speaking, more the distance, more the fare. The distance is more than the fare will be more. That's the other inference we can do.
Sir, like how Ola, Ubers, and other like Zomato, all these deliveries guys finding shortest path of the particular location.
Distance. That is using Google Maps API. They're not building the mapping engine by themselves. That is using the Maps API completely. So I give you point A, I give you point B, right? Now, who is that? This
Saurabh.
is Saurabh. So there are multiple ways you can go from A to B. If you see there are road networks here also. There are road networks here also. There is a road network. I could have gone like this also, right? There are infinite number of ways I can go from A to B. Okay, even in this mapping system that you can see, there are multiple paths I can take, right? If I move the marker somewhere here, maybe it will be easy to understand. If I move the marker somewhere here, so there are multiple ways I can go. Now I could have gone like this also. I could have gone like this also. I could have gone like this also. Out of all these different paths I could have taken, it will pick the shortest one. Shortest one based on the distance. Simple, straightforward. How is it done? That is through the APIs. That is through the mapping APIs. Google Maps will charge you. OSRM does not charge you. Apparently, there's a Python. There's a Python. This one, what do you call? There's a Python package called OSRM also that you can use. You can pip install OSRM, and it is very simple to use it. You can see, I can import OSRM. You can first pip install, then you can import, and then it's just a matter of doing this. Very simple. Just give the route, OSRM.simple route. Give the latitude, longitude coordinates. This is my lat long pickup. This is my lat long drop off, and the model will give you the complete distance and the geometry. Geometry will give you the shape. That shape, no, like it is like a kind of may or may not be a polygon. So it's a shape like this, then this, then this. So the vertexes will be given to you. The coordinates of the vertexes will be given to you. Like to travel from A to B, what is that coordinates that you're following? You can actually plot a chart also in Matplotlib. You can do that with a mapping background. But what we need is just this. We are not concerned about geometry right now in the class. We just need this. We just need to know that, hey, to travel from here to here, what is the shortest distance that is taken? So the APIs will directly give it. Right? I hope that clarifies. So mapping engine is again a different ball game. So to answer the short part of your question, how are they getting the distance? That is through the APIs completely. Getting a little deeper, how has Google created that engine? That is using reinforcement learning. So that's a machine learning that they have done to generate that at the backend. Actually.
Okay, sir.
Yeah. Let me also ping this to you because some of you might be curious about these mapping projects. Coming back, so we have incorporated distance and we are getting a better model. We can also potentially add airport-based features. What we are doing is now we are adding airport trips as features. So based on the features of the ride, we are saying, is it an airport ride, airport pickup, or airport drop-off ride? That is what we are saying. So there are 3 airports in New York City: Newark, LaGuardia, and John F. Kennedy, JFK. So there are overall, there are 3 airports in New York City. So we have Newark Airport, we have LaGuardia Airport, and we have John F. Kennedy, JFK International Airport. And we are basically tracking for each of the rides. Is it a pickup from JFK? Is it a drop-off at JFK? Is it a pickup at Newark? Is it a drop-off at Newark? Is it a pickup at LaGuardia? Is it a drop-off at LaGuardia? So we are basically looking at the different attributes of the ride and tracking. Is it a pickup ride or is it a drop-off ride? Is it a pickup ride, drop-off ride, or is it a pickup ride, drop-off ride? That's what we are tracking primarily. Okay, so we're adding airport trip related features. And why is it important? Because once again, keeping every other factor constant, if I know it's an airport ride, if it's an airport pickup or airport drop, then the fares will be higher. So that is exactly what we are seeing here also. The fares have increased. And what I wanted to show you through this exercise, and finally the last part is adding Borough-based features. Borough is nothing but locality. So if you're in Bangalore, from the latitude, longitude, I can get to know what part of Bangalore you're from, or where are you booking the ride from, and where are you. So if you're booking a ride from Outer Ring Road, Belandur, Sarjapur Road, that horrible section, that traffic jam area. So you're booking a ride from Sarjapur to something like Yarpuram at 5:30 p.m. You'll be there for 2 hours, guaranteed. Okay, or maybe you can relate to Bombay. Certain parts of the city, based on the locality, will have very different fare patterns, either based on the traffic or based on the poshness of the area, something like that. So maybe in Hyderabad, Jubilee Hills is a very posh area compared to old Hyderabad. Is how it is. It's the reality, basic. Okay, maybe something like a Madhapur is not that posh as Jubilee Hills. Jubilee Hills is one of India's costliest real estate. some of the most expensive apartments are there in Jubilee Hills today. After Jubilee Hills, then comes Bombay. That's how the research goes. So yeah, so from latitude, longitude, we can go and find out Borough-based features and see how we have added these Borough-based features here. Pickup is from here, drop-off is here. So again, why are these important features? Because keeping everything else constant, these are good predictors of fare. If I know what is the pickup location, if I know what is the drop-off location, I can accurately predict the fare. If I know what is the pickup, what is the drop-off, I can accurately predict the fare. So certain areas, the fare will be inherently high. Other areas, the fare will be inherently low. So knowing the pickup and drop-off locations will help us estimate the fare a lot more accurately. So that is the the problem that we can solve with this. All right, I hope this is clear. Everyone's getting. So the key takeaway from this exercise would be, again, the feature engineering bit, where we started off with a data set that was completely raw, completely dirty. There was nothing we could have done with it. There were no good quality features we had. And we started generating features from here. So from here, time-based features, distance features, airport features, Borough-based features. Is it a long trip? Is it a short trip? So many features we have created. And this is what I wanted to clarify, that machine learning projects are like this. Next time you're working on a real-time project and you're wondering, sir, why is it taking time? Like, we can run the model.fit in 2 minutes and we can build a model. But what is really taking time is this experiments. You're constantly performing different experiments on your data. You're constantly trying out different things and trying to build better quality models over time. And that's why they take time. That's why, that's the reason I wanted to highlight here. All right, so I hope all of you have managed to read through this data set. And once again, something I was mentioning at the beginning of the exercise. So this is a lead scoring case study we are doing, and this is pretty much the business context. So you can see this is pretty much how things were happening before. We have 100 leads, and you can see how things were happening before. So we have 100 leads, and the typical outbound customer support will call up each and every customer manually. So if you look at it from a customer support perspective, all the customers are being manually called right now to start with. Okay, so to start with, all the customers are being manually called. So 100 leads we have got. So we've got 100 potential customers, and we are calling all the customers manually. And let's say the support agents are spending 5 minutes per lead, and overall we are getting 2 converts. That is what is happening in the process, right? This is the thing that is happening right now. 100 leads, 5 minutes per lead, and we're getting 2 converts. Very inefficient. Now, how does machine learning help? Machine learning says that, okay, I will give you the same 100 leads, but this time don't call each and every one of the leads manually. No need to call them manually. Rather, what you do, you take those 100 leads, pass those 100 leads through a machine learning classifier, and find out the probability of convert. Right? So take those 100 leads, pass it through the machine learning classifier, and find out what is the probability of convert. So this is a classification model that we will use to figure out what is the probability of convert. And if the probability of convert it is more than 30%, then we will send it to one set of salespeople. If it is between 10 to 30%, send it to one more set of salespeople. And if it is less than 10%, then discard those leads. That's the way how we will approach it. Right? I hope it is absolutely clear to you. So instead of doing a random cold calling, we're taking the same 100 leads. This will go through a classification model. And based on the features of these potential customers or the leads, we will try to predict what is the probability the lead will convert. So if the probability of conversion is more than 30%, that means we are very confident that the lead will convert. If it is a very high probability of conversion, then what we will do, we will send it to one set of salespeople. We will channelize those leads to one group of salespeople. If the probability of convert is between 10 to 30%, then channelize that to one more group of salespeople. And if the probability of convert is less than 10%, then discard those leads. Those are leads that we will discard and that is not needed. That's the way how we look at it. So out of the 100 original leads that we had, 90 of these leads we are straight away discarding. Why? Because their probability of conversion is very low. And we are eventually proceeding ahead with the conversation only with these 10 leads. And out of these 10 leads, we are calling up these 10 leads and getting overall 5 converts. That is what is happening in the process. So out of these 10 leads that we have, we are calling up these 10 leads and we are getting overall 5 converts. So this is the business perspective of the exercise. Don't try to uh, approach this from a technical perspective. The technical part, I always say, comes a lot later. But you should always approach the things from a business perspective. That initially, it was a very costly process for the organization. We were having to call all the 100 customers, potential customers, without any results. You were investing a lot of time on the support people. They're making calls, but they were not getting results. But after we use machine learning, the 90 are straight away discarded. You're effectively only making 10 calls and you're getting 5 converts because these are more motivated people and they're able to more proactively convince customers to join. So the cost has reduced and the revenues have increased. So the profitability of the organization has gone up. And every machine learning project that you're involved in, starting right from your, whatever you have done probably in your course, credit default prediction, and all these use cases you have seen, there is always a business angle to it. There is always some kind of cost savings. There is some kind of a profitability computation that you'll be able to do there. If you are unable to do that, then that is a very clear indication that project will never sail through. So it is very important to understand how is the machine learning project actually helping the business stakeholders. Because I have done so many projects in my career, and I've actually seen machine learning right from its inception, for a very early time. And I've seen a lot of POC projects. Management and the upper management does not give funding, and they just freeze those projects because they don't see the business value. So see, as project engineers and project developers, we see it's cool that hey, it's a great idea. Why don't we do this? But you know how the management sees it? The management says that okay, great, yes, there's a solution that we can do, but then okay, you tell me what is the profitability? Why should I pay science so much money as a data scientist to develop this? What do I get in return? How is the company benefiting? Why do I need to hire a big data science team and get this particular project done? But how is the company getting profitability out of it? If you cannot convince that, then oftentimes those projects mostly stay in POC stages. So make this a very important part of your presentations and conversations also. Right? How do you bring out that cost aspect as well? If I take the liberty of adding a couple of more points, all of you know this is a classification problem. And in classification, we have something called false negative, false positive, all those kinds of conversations we have. Now, what is false negative? False negative is basically very, very costly here. Model predictor, you will not convert. In reality, you do. So I'm sure you agree, FN is extremely costly here. Whereas false positive is kind of comparatively less costly. False positive is okay. FP is fine, but false negative unacceptable. Okay, so that is another thing I want you to keep in mind. Now, coming back to the solutioning, let us come to the solutioning, how I've done it actually. Let me just walk you through a couple of pieces of that as well. Let us see that as well in action. This is the solved case study and standard classification problem, no rocket science. We will recap some of the ideas of classification in a different case study. We'll see that, but this one is again, there are a few new ideas I will introduce here also. So let me first run this for you and let me show this. Just allow me a minute, please. Okay, so first I need to mount that G drive. This is first thing I have to do, or I think I'll just take the path directly from here. Okay, I already solved this one, right? So this one here. Let me just take the path from here straight away. All right, this is the lead scoring one. I'll just quickly load into Collab and access my data set here. And this is the link I will give. Okay, it will be very similar, just that here I will have to say lead scoring case study. That should be fine. Okay. All right. So this will be lead scoring case study. I guess that's the name. Let me check. Yeah, lead scoring case study. So make sure that you are changing these in your drive also. And actually, there's a better way of doing it. I know I'm just showing some exercises and demos right now in the class, but honestly, there are better ways of doing it. So it's not a good practice to change paths like this. So what we do is we make the process more dynamic. We create environment variables. All of those things are actually done. So we create some global variables at the top and you keep the paths there. And what we do is we never use static values here because otherwise these kinds of problems will happen. You will have to change it each and every time. Okay, so this is not a very good practice, but I'm just showing you as a demo. But yeah, I mean, you get it all of you, right? So let me just run this for everybody. This is my leads data set, and as you can very clearly see that we have got these are prospective customers. Every row corresponds to a prospective customer, and we have the features of the customer, right? So we have the lead origin, where the lead originated, what is the source of the lead, um, how much time spent on the website, how many page views per visit, what is the lead profile, what city they belong to. These are the different attributes of the lead. The total number of visits on the web page, how much total visits they have done. So all these are the different features of the lead. And if you just scroll to the right, we have got last notable activity. What is the last notable activity for the lead and all that? I agree to pay the amount through check. So has the lead agreed to pay the amount through check? Yes, no. So all that. And based on that, we have the output column converted. And converted says that did the lead convert? Yes, no. So based on the features of the lead, we are trying to figure out whether the lead will convert or the lead will not convert. That is what we are trying to predict. So every row stands for one lead, and we are looking at the different attributes or different features of the lead. And these are the features of the lead that we see on the screen right now. Okay, so each and every row corresponds to the different attributes or the different features of the lead. That's what we are saying. And based on the different features of the lead, we are trying to predict whether the lead will convert or the lead will not convert. That is what we are trying to do here. That's the binary classification problem. Okay. And this data has been taken from a past marketing campaign. In case you're wondering where is the original data taken from, the original data has been taken from a kind of a past marketing campaign. So some past marketing campaign has happened, and this data has been taken from a past marketing campaign. That's the inference we are able to get right now. All right. Now moving on. So first we'll create a Sweetviz report on this data set. Let us just quickly go and do this. So Sweetviz is an Auto-EDA library. So oftentimes we have done exploratory analysis in a very manual way. And what you're able to see right now is we are using something called Sweetviz, which will help us generate visualizations automatically. This is like really cool. And you can see it automatically analyzes the whole data. It figures out what all columns are present, and it understands the data that is present in the columns, and it will automatically create a lot of charts for me. This is what is done in Sweetviz. There are many such Auto-EDA kind of libraries that we have, and I'll give you a bit of a sneak peek into some of them. This is one such example I'm showing you, and you can use it for any data set. Any data set you take in, you can run Sweetviz and you can generate an auto report. And after this executes, what will happen in your working directory? An HTML file will be created. You can see in my working directory, after this runs, after this completes execution, the sweet report.html will be created. I can refresh, and now I can download this file, and I can actually see the contents of the file. I can see what has been created. And you'll be surprised to see a very beautiful visualization of my data within a matter of seconds. Okay, so this is a very beautiful visualization of my data we are able to see in a matter of seconds. We are able to see. So number of rows, number of columns. For the numerical columns, you are able to see it usually does distribution plots. So there are distribution plots that we are able to see for the numerical columns. And so yeah, so just to clarify, for the numerical columns, we are able to see distribution plots. And like for example, total time spent on website is a right skewed distribution. Okay, so most of the values are average to low, and few values are extremely high. So we are able to see a kind of a right skew distribution for total time spent on website. So this is an example of a right skew distribution we are able to see. Okay, uh, so most of the values are average to low, and few are extremely high. So right skew we are able to see total time spent on website. And so yeah, for all the numerical features, we are seeing a right skew. Categorical features. The categorical features we are able to see this thing, value counts. Now, what I wanted to particularly highlight here in this exercise is features like this, because mind you, these are all features, these are all input x's. Output is converted. This is what we are ultimately trying to predict. This is the value that we are trying to predict. Will the person convert or not convert? Now, the question is, what is the inference you can make for features like this? So there's a particular feature called I agree to pay the amount through check. And you can clearly see that everybody has answered no. So again, the column I agree to pay the amount to check, everybody has answered no for that particular thing. So my question is, what inference do you get for this one? Can we say this is a good feature? Can we say this is not a good feature? So what can we say? Just by looking at this, what can we say? This is the feature. So is it a good quality feature? Is it not a good quality feature? What can we say?
It's not a good quality feature.
Not a good quality. Okay, why do you say that? Why do you say that?
It doesn't actually give any differences between what we are trying to infer. Like it doesn't. It has only one static value. So we know that everybody has an opinion of not paying through check. So
Hey, I think I lost.
1 minute. I'm sorry. I'm so sorry. I just lost you there for a minute. Can you repeat again? Sorry. Can you repeat again? What did you say?
So it doesn't significantly show any difference between values. So we know only one value is there and everybody accepts to it. So it doesn't improve the model at all.
Okay, fair enough. Absolutely, absolutely. So if I have to use a more technical term, this is actually called a zero variance feature. These are called zero variance features. In fact, this is also a kind of a feature selection technique that we use, apart from all your p-values and feature importance. If you see a big data set like this, especially this kind of a data set, and especially if you've got categorical columns, look out for features where the variance is either equal to 0 or near 0. And as you rightly said, this feature does not show any variation. That means, imagine that we have this feature, I agree to pay the amount through check. Let's say this is my feature X. And we are trying to predict, let's say we are trying to predict, will the person convert or will the person not convert? Converted is what we are trying to predict. So based on this, we are trying to predict converted status, right? Now think of it this way, the check value is always equal to no. Look at it. Imagine if I only take this feature to predict the output Y. See how bad a feature this is. All the values are no, right? Now, the converted could be yes, the converted could be no, right? So some customers will convert, some will not convert based on other factors. The check value has nothing to do with converted status. So by using this X, we will be unable to predict the Y. So just by using this particular X, can I accurately predict the Y? No, I cannot. That is what I wanted to clarify here. Okay. So just by using this particular input X, we are not in a position to accurately, because the feature is not having any variance at all. The feature is effectively having, just to clarify, the feature is effectively having zero variance. And because the feature has zero variance, we will say that the feature X is not a good predictor of the output Y. Because ultimately, as I said, you want to predict the converted status. Did the customer convert? Did the customer not convert?
right? So the converted status is what we are trying to predict. So whether the customer converted or whether the customer does not convert, that depends on other factors. That does not depend on your check status. This is no. For all the customers, this is no. So this has nothing to do with whether the customer will eventually convert or not. And you will see that there are a lot of such features. Like even this is a zero variance feature. This is a zero variance feature. And oh, is it a zero variance feature? No, it is not. But I would say this is a near zero variance feature. Okay, so this isn't a zero variance feature per se, but I would say this is like a near zero variance feature. Okay, so what is it exactly? This is like a near zero variance feature. That's what we are able to infer right now. What that's the idea. Okay, near zero variance feature. And even these kinds of features we can drop from the analysis. So I think overall we have a data set with around 37 features, but we can already start to see that by going and doing this kind of pre-processing, we can easily drop the number of features, which I will do now. I'll quickly do that for you now. I'll go back and remove some of these columns and do the pre-processing for you once again. See, this is the same thing I've written here. You can see, since practically all of the values are, or these variables are no, it is best that we drop these columns as they will not help in our analysis. This is how we are dropping some of these zero variance columns. This is exactly what we are doing. So we'll go and drop all these features particularly. And let me go and drop it now. And let me do the Sweetviz analysis on the revised data set. Let me see how it looks like. Original data set we already did one. And now this is the Sweetviz analysis on the revised data set. Let us see how it looks like. Oh, what's the challenge here? Just 1 minute. I think this is a problem. Just 1 minute, please. Some challenge here. What is the challenge? Let's see. Delete dot drop. What happened? Positional argument. Huh? Access equal to 1 will happen. So access is not taking. Just 1 minute, please. Okay. Control enter. Now it's fine. Oh, I think it did not recognize that actually. That's okay. So leech dot shape, and now sb dot analyze. Now it will work fine. Now after I've cleaned and transformed my data, now let me regenerate my data frame, and now we will do the entire classification on the revised data frame. Okay, let us see that. Once again, you can look out for the working directory, and the suite report HTML will be updated. This is an updated HTML file now. You can download that. We can open that up now, and you can see it looks a lot cleaner than before. And you can see there are only 18 features now, not the original 37. We have almost reduced the number of features by half now. We've got only 18 features now, and you can scroll all the way down and see, the features here. And now our data is ready for classification. And now it's a standard stuff. It's just a standard stuff where we are going and building a logistic regression model. And you're seeing the training and testing accuracies of around 70% on, which is, I think, reasonably underfit model, not a very good quality model. And there is a scope to make it better. Definitely, there's a scope to make it better. And this is the confusion matrix that we're able to see. Okay. One more very interesting idea. I hope this part is clear. This is the general classification flow, supervised learning flow. People are comfortable. I'm not taking you through the code snippets because this is straightforward stuff. I hope everyone can relate to it. So first, we have done the train test bit already at the top, and then instantiate logistic regression. LR.fit explain y train. You're fitting the model on the training data, and you're calculating the scores on the training data and the testing data. So we are calculating two different types of accuracies. One is the training accuracy, and two is the test accuracy. The training accuracy means how well the model is performing on the training data. So whatever data the model has been trained on, how well the model performs on that. That is what we call the training accuracy. And we also have the test accuracy. The test accuracy tells us the performance of the model on the unseen test data. That is what we call the test accuracy. How well the model is performing on the unseen test data, the test accuracy. And we can create the confusion matrix on the basis of that. Okay. This is very interesting. This is called the validation curve. This again might be a little new to some of you. Validation curves come in very, very handy, especially while hyperparameter tuning. Okay, so this kind of thing comes in very, very handy, especially while you're doing hyperparameter tuning. So during hyperparameter tuning, this thing comes in very, very handy. And once again, you can clearly see that in this validation curve, along the x-axis we have something called depth. Okay, so there is something called depth along the x-axis, and there is something called accuracy along the y-axis. Depth is a hyperparameter for a decision tree. You might know maximum depth of a tree, and I think we can all relate to it that the lower the value of depth, as the value of depth is less, the model will be typically very underfit. And as we increase the value of depth, the model will become more and more overfit. So maximum depth for a decision tree is a hyperparameter, and as we for lower values of depth, the model is significantly underfit. And for higher values of depth, the model becomes more and more overfit. If the depth of a decision tree increases beyond the point, the model will become significantly overfit. So the gap between the training and testing accuracies will increase drastically. That is what will happen usually for a very high value of depth. Whereas for a low value of depth, the training and testing scores both will be extremely low. So that is what will happen for a lower value of depth generally. What we are trying to do is we are trying to find out what is the optimal value of depth where we have the best model. So on one extreme, we know what happens for lesser values of depth. We know what happens when the depth becomes very high. And what we are trying to do is figure out uh, what happens exactly in a scenario where where are we getting the best model, for what depth value we are getting the best model. This is the same thing we do in hyperparameter tuning also, right? We use grid search CV, we give a parameter range, we do the same thing. This is just a visual depiction of that. Okay, so try to use the validation curves in your project also, and you can use it for any algorithm. It is not specific for only decision trees. You can use it for decision trees, ridge, lasso, regression, other algorithms also you can use it. Okay, the code snippet is very simple. Again, don't be intimidated. This is all matplotlib stuff. Just like that silhouette code. This is all matplotlib stuff. Don't worry. The main code snippet is just this one. This is the only simple code snippet for validation process. This is all it is. Okay, so learn model selection validation process. You give the name of the algorithm. What is the algorithm that you are trying to use? You also specify the X-frame, Y-frame, the parameter name. What is the name of the parameter that you are trying to tune? Okay, so specifically, what is the name of the parameter that you are trying to tune? So here we are trying to tune maximum depth. So please specify that, and it will automatically generate the scores for you. Okay, so this is again, I found it very useful, especially when you want to visually see the progress of your model, because hyperparameters are very difficult to tune, and oftentimes it's not possible. How will I even know what is the range of hyperparameters to take? I'm sure that's a question people have at the back of your mind. Like, sir, I want to tune a decision tree, or I want to tune a random forest. How do I know what is the estimator's range I should even take? It is random trials. There's no rocket science about it. You have to try, it's trial by error. But then this gives you at least some visualization. At least better. It's better to have something than nothing, right? At least you're able to visualize that, okay, beyond maximum depth equal to 10, definitely the model is overfitting. You will definitely not go beyond 10. At least if you're able to plot it, you will be able to see the progress. That, okay, beyond this hyperparameter value, the model is certainly overfitting. So I will not go beyond that point. That's the idea. Right? So otherwise, it's a simple binary classification problem. And very clearly with logistic, we got a model that looks somewhat like this. With random forest, is a little better. Random forest, the model has incrementally become a little better. Training and testing scores have slightly gone up. And one more very important takeaway from this thing is something called class weight equal to balance. I wanted to take a minute and talk about this also, friends. Okay. Now, what is this? Now, this is an extremely useful thing that we use, especially while working with imbalanced data. Right? So, what is class imbalance? I'm sure it's something you guys have heard of. Class imbalance is a problem where we have a lot of data for a particular class, but we have very little amount of data available for another class. That is what is referred to as class imbalance. Right? So, if you're looking at a gradient boosting classifier or a random forest classifier, we have a lot of data that is available for, like in this particular example, if you see, let's say there are 100 potential leads. If I take, let's say if I give you overall 100 leads worth of data, then we will see that out of 100 leads, only 5 have converted, but 95 have not converted. If I give you overall 100 leads worth of data, only 5 of the leads have converted, but 95 of the leads have not converted. That is the inference that we can make out of it. Okay. So out of 100 leads worth of data, only 5 of the leads have converted, 95 of the leads have not converted. That is the inference we can make out of it. That is what we are able to get right now overall. So this is again a very clear case of what we refer to as class imbalance. Okay, so class imbalance again is a problem where uh, there are a lot of records of a particular class. So there are 95 records of the not converted class, but there are only 5 records of the converted class. There are only 5 people who actually converted. So that is class imbalance. Now, what is the way to handle that? One of the approaches that we use is called oversampling. Right? I'm sure some of you might have heard of it. It might have been discussed very briefly before. So there's something called oversampling we use. And specifically, we use techniques like Mote. Mote is actually used as one of the techniques for a long time. And nowadays, what we do is we use Gen AI a lot. If you talk about the industry today, in industry, we today use generative AI techniques to synthesize artificial data of the minority class. Okay, so let me just bring up that diagram once again for you. If you see, I think it will be better to visualize and see this. If you look at the data set right now, very clearly there's a tremendous amount of class imbalance. Can you see? Look at the converted status right now. Out of 90 to 40 records, 60% of it is not converted, only 40% is converted. I'm not saying this is a huge amount of class imbalance, but still there is some class imbalance. Okay, the output class, most of the records are not converted, but few are converted. Let's say. One way to handle that is we can artificially create more records, or we can artificially create more data for converted. Okay, so for the converted class, we can artificially create more data. And we can use oversampling, or we can use Gen AI techniques today to do that. That is one way to do it. Now, the problem with artificial data generation is many domains are okay. Companies are, I think today techniques have become better, but it is still a problem area. And it used to be a big problem area in before also. Because if you're looking at highly sensitive domains like finance, I'll give an example. Let's say finance data. See, marketing is again not that sensitive. This is okay. But finance is very sensitive. If you're looking at credit card fraud detection or credit card default prediction, you will have data imbalance. You will have class imbalance there. Out of 100 customers, only 5 will default, 95 will not default. So there is a class imbalance. Output class is imbalanced, right? What do you do? So the only option you have is to artificially create more data. So what are you actually doing? You're artificially creating customers. Right? Now those customers are not even part of the bank, but just for your model to work, you're artificially creating more customer data. So that's a red flag. These things are sometimes not allowed in compliance processes in real organizations. And so generally, artificial data creation is something that you should try to avoid if you can. And for that, what we do is instead of handling the problem at the data level, we try to handle the problem at the algorithm level. So we are saying that even if our data is imbalanced, even if our data is class imbalance is there, it's okay, let it be. I will go and I will tweak my algorithm. And while my algorithm will give out predictions, during the prediction time, my algorithm will give higher weightage to the minority class. That's the thing. Okay, so during the prediction time, while my algorithm will do the prediction, okay, so while my algorithm will do the prediction, it will give more weightage. It will give higher weightage to the minority class. More weightage will be given to the minority class. That's the idea. Minority class here will be, not converted. So while the prediction happens, the final random forest prediction when it's happening, the voting is happening and all that, the weightages that will be given, it will give a more weightage to the minority class. That is what it is. Okay, so this is just one approach I wanted to talk about, and then this will generally help you get good results. You can try this out. Very simple, even without understanding too much of the tech, or if you just incorporate this in the code for all your classification algorithms, you will actually get pretty interesting answers, pretty good answers actually. Okay, so try to do it. And then after that, what I've done is use the same validation curve with other algorithms, gradient boosting, random forest, and just trying out different algorithms. The same classification stuff that you're seeing all through the courses so far. Right. So here I'm using a validation curve. I've got estimators along the x-axis, and I've got the accuracy along the y-axis, and we are able to clearly see, as we understand that, as the number of estimators is less, the model is highly underfit. The training and testing accuracies are very low. We have a highly underfit model for when the estimators is less, and as the number of estimators increases, the training goes up, the testing also goes, and beyond the point, as the number of estimators crosses beyond the point, you can see the training actually goes up and the testing actually comes down. Cross validation means testing. Cross validation is an average test accuracy, right? So beyond the point, you can see that there's a breakaway that's happening. So you get a very beautiful visual idea in terms of where is the model starting to underfit, where is the model starting to overfit, and you get a very nice overall visual depiction of the whole thing right now. Right? I hope this is clear. Everyone's able to understand this so well. Okay, so this is just one other. So the key takeaway from this exercise was not classification. I think the algorithms and all are standard stuff you've seen. So two main takeaways. One was obviously the business aspect, how to think from a costing perspective, from a profitability perspective. The second important takeaway was, I think, Sweetviz was a bit of a new learning probably. Third important was we understood how to look at zero variance features, features which do not add any value. If you have a particular column and all the values in that column are exactly zero, then you should go and try to draw those columns. Okay, so that is one kind of feature selection technique used. Okay, and finally we looked at the idea of class imbalance. How do we use class weights to handle data which is highly imbalanced instead of artificially oversampling the data, instead of artificially generating data, which is a bit of a risky area. You're artificially creating something that never existed. That's a risky area, right? Instead of doing that, we are using the algorithms to give a higher weightage to the minority class, which is a much safer approach and actually a more accurate approach we have seen with testing. Okay, all right. So because one thing I'm very clear is even when it comes to artificial data creation, the problem is the distribution of the data will still be the same. Yes, class imbalance will be there; it will be rectified. That's one part definitely. But one of the things about artificial data creation will be that the overall like even if you're artificially creating the data, the distribution will still remain the same. The characteristics of your data will remain the same, not that your data is inherently changing. So those things you cannot take away. Right? That's just one thing I wanted to clarify with all of you. So this is just one other case study I wanted to share with you. Some key ideas. One more important thing I encourage people in the audience to do. You can look up Kaggle case studies and do some practice from there also. But I think there is um, one of the things I would like you to do is to work on problems which involve joining data from multiple sources. Like in all these exercises, what we have majorly seen in the course and the curriculum and also the case studies, because we have limited time, actually only 2 days. So what we are mainly seeing is that we are mainly seeing data sets where a single data set is given to you, either one CSV file or one Excel file or an XML file or something of that sort is given to you. And you're required to build a model using that data. That is how it is usually, right? Now, what I am proposing is I'm saying that, okay, so I'm saying that, okay, why don't you go back and see problems where you're actually getting data from multiple sources. How do we actually work on problems where multiple sources are involved? That is also very important. And remember, all the algorithms that we discussed, whatever algorithms we have in regression, classification, and all these kinds of things that we are seeing, they are all meant to work on a single data frame. It is not that when we eventually build a regression or a classification model, we can actually work with multiple data frames. We cannot. Eventually, all the algorithms we use, all those algorithms will eventually work on only a single data frame. Please be very clear on that. They will only work on a single data frame going forward. You have to ultimately, the very first step, that's why we say data engineering is so important. The very first step is taking the data from multiple sources, converting the data into a single data frame, and then building a model on top of that. So sometimes even that approach will come in very, very few. Okay, so just be very, very clear with some of those. There's a lot of very, very nice competitions on Kaggle that we also, if I have to give you maybe one such example, I can take one example competition. This was a competition that was conducted by Walmart. It's a Walmart store sales forecasting competition. What I particularly like about this competition was how varied the data sources are. See, they have eventually given us everything in a single data frame form, but if you're looking at the engineers at Walmart, what they're actually doing, because I've myself done some consulting at Walmart, I know what kind of data is being worked with there. So if you just look at the data set to predict store sales, so historical sales data is only one part. It is not just the historical Walmart data that's needed. To predict the sales in this Christmas New Year time, Walmart also needs to understand the macroeconomic aspect, like what is the fuel price, what is the employment ratio in the United States, what is the GDP per capita, what is the inflation, what is the unemployment rate, the inflation, consumer price index, interest rates, Federal Reserve, what kind of policy decisions they are making. Because if the economy is not great, then obviously people will not buy. you're also going to have to take into account the temperature, because if there's a lot of snowfall and in the streets, and people will not come out and go to Walmart stores and buy something, right? Fuel price is a very important factor. So these are very, very important things to keep in mind. Wind speed, all those kinds of things. Stock markets, how is the S&P 500 doing? How is the Nasdaq doing? What are the geopolitical aspects? If there's a global war that breaks up between, like, we are seeing Israel, Iran, and all that happening, right? So even those aspects are very, very important in the geopolitical, the macroeconomic aspects are extremely important in Walmart sales. Because if a war breaks out, economy will be impacted. If economy is impacted, people will lose jobs. If people lose jobs, they will not have money. If they don't have money, they cannot go to Walmart and buy something. You're already starting to see how so many of these things are taking into, like, adding up. So these will be different data sources, right? So Walmart is having their own sales data. Weather data will come from somewhere. Macro data will come from somewhere. Yahoo Finance or Bloomberg terminal data will be taken from stock markets and all, right? So, and based on that, you will try to predict the future sales. That is why data engineering is such a complex challenge. So in all data science projects, this is usually the first starting point. That's why we say we try to have a project manager involved right in the beginning, figure out what kind of silos of data we have, get all of it into one data store, and then this is where the data science team actually takes over. Then they start doing all the EDA and modeling. Okay, all right. Just wanted to give a brief picture on this also. And usually these are pretty complex. Some of you are working on SQL Server databases and all. So instead of having like Excel files and all, you might have the whole data that is present in a database, or it might be present in a data warehouse or a Hadoop system. So you have to actually navigate those complexities and first of all be able to read the data. Only then all the other things will take over, right? So just wanted to clarify this aspect also. This is a very interesting competition, and companies are very actively hiring people to this competition. See, look at this. If you wish to be considered for an interview, allow the host to contact me. This was long back. This was more than 10 years back. So the processes are a lot more established today. Kaggle is actually a very, very good hiring platform as we speak.